Right now, as you sit there watching this video, invisible forces from the deepest reaches of space are racing toward Earth at the speed of light. We've built our entire civilization believing we're safe, protected by our atmosphere, shielded by distance, insulated by the vast emptiness between us and the violent cosmos beyond. We go about our daily lives as if Earth exists in some cosmic sanctuary, untouchable and secure. But what if I told you that's the most dangerous illusion humanity has ever believed? What if our planet is actually suspended in a cosmic shooting gallery, where weapons of unimaginable power can strike without warning? What if the very technologies that define our modern world, our satellites, our power grids, our communications, could be wiped out in minutes by forces we can barely comprehend? The universe is filled with phenomena so terrifying, so utterly destructive, they make our worst nightmares seem like gentle dreams, gamma-ray bursts that can sterilize entire star systems, polar storms that can bring civilization to its knees, asteroids that have already reset life on Earth and will do so again. Join me as we explore the most terrifying threats lurking in space and discover why, despite all our technology and knowledge, we are absolutely not safe. Before we venture into this cosmic horror story, I'm curious, where in the world are you watching from right now? And what time is it where you are? Drop your location and local time in the comments below. It's fascinating to think that no matter where we are on Earth, we're all equally vulnerable to what's coming from space. Picture Earth from space, that beautiful blue marble suspended in the cosmic dark, wrapped in swirling white clouds. It looks peaceful, doesn't it? Serene, protected. That image has shaped how we think about our place in the universe, creating what might be the most dangerous misconception in human history: the belief that we're safe. For most of human existence, this illusion served us well. Our ancestors looked up at the night sky and saw beauty, mystery, divine patterns. They had no idea they were staring into a cosmic war zone where forces of unimaginable destruction play out on scales that dwarf our entire solar system. They couldn't know that the peaceful twinkling of distant stars often masks the most violent events in the universe. Our atmosphere seems solid, permanent, like an impenetrable wall between us and space. Every day it shields us from cosmic radiation that would otherwise sterilize our planet's surface. It burns up countless meteors before they can reach the ground. It maintains the perfect pressure and temperature that allows liquid water to exist. This invisible guardian has protected life for billions of years, and we've grown complacent in its embrace. But here's what most people don't realize. Our atmosphere is shockingly thin. If Earth were the size of an apple, our life-supporting atmosphere would be thinner than the apple's skin. That gossamer layer, barely 60 miles thick, where it matters most, is all that stands between us and the killing vacuum of space. It's not a fortress. It's more like a soap bubble in a hurricane. Then there's our magnetic field, that invisible force that deflects the solar wind and cosmic radiation away from our planet. We call it our magnetosphere, and it extends far into space, creating a protective cocoon around Earth. When solar particles hit this magnetic shield, they're guided away from us, often creating the beautiful auroras we admire at the poles. It's an elegant system that has worked flawlessly for eons. But magnetic fields aren't permanent. They weaken, they fluctuate, they can even reverse completely. Mars once had a magnetic field like ours. Venus might have had one too. Today, both planets are lifeless wastelands. Their atmospheres either stripped away by the solar wind or transformed into hellish pressure cookers. Our magnetic field has weakened by 15% just in the last 200 years. What happens when it weakens further? What happens if it fails? The cruel irony is that the very technologies that make us feel most secure, our satellites, our GPS systems, our global communications networks, are actually the most vulnerable to cosmic threats. We've built a civilization that depends entirely on delicate electronics, and we've placed much of that infrastructure in space, completely exposed to whatever the universe wants to throw at us. We live in what scientists call the Goldilocks zone. Not too hot, not too cold, but just right for life. But this zone isn't a place of safety. It's a target. We orbit a star that regularly unleashes devastating storms. We're embedded in a galaxy filled with stellar explosions and wandering black holes. We share our cosmic neighborhood with asteroids and comets that have already caused mass extinctions. Our safe position is actually a front row seat to the greatest show of destruction in the universe. Imagine you're standing in the middle of a battlefield where invisible snipers fire continuously from every direction. Artillery shells explode without warning, and landmines dot the landscape. Except this battlefield is the size of the observable universe, and the weapons can destroy entire planets. That's where Earth exists every single day. Our galaxy, the Milky Way, contains over 100 billion stars, and stars are not the gentle twinkling lights they appear to be from Earth. They're massive fusion reactors, some over 100 times larger than our Sun, burning at temperatures of millions of degrees. When these stellar giants die, they don't fade quietly. They explode with the force of 10 billion atomic bombs, detonating every second for millions of years. These stellar explosions, called supernovas, happen in our galaxy roughly once every 50 years. Each one releases more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. If a supernova occurred within 30 light-years of Earth, a distance that sounds enormous, but is actually our immediate cosmic neighborhood, the radiation would strip away our ozone layer and bathe our planet in lethal cosmic rays. But supernovas are just the opening act. Some dying stars create something far worse: gamma-ray bursts, the most energetic events in the known universe. These cosmic weapons can focus the power of 1 trillion suns into a beam of pure destruction that can reach across billions of light-years. A gamma-ray burst pointing at Earth could end life as we know it from halfway across the galaxy. Our own star, the Sun, seems stable and benign, but it's actually a variable star that regularly unleashes coronal mass ejections, billion-ton clouds of magnetized plasma hurled into space at millions of miles per hour. When these solar storms hit Earth, they can overwhelm our magnetic field, disrupt our satellites, and induce electrical currents powerful enough to melt power transformers. The largest recorded solar storm, in 1859, made telegraph wires spark and set telegraph offices on fire. If a storm that powerful hit today, it could send our technology-dependent civilization back to the pre-industrial age. Then there are the asteroids and comets, leftover debris from the formation of our solar system, whole solar system, still careening through space like cosmic bullets. NASA has catalogued over 28,000 near-Earth objects, and they discover about 30 new ones every week. These aren't distant threats, they're our neighbors, following orbital paths that regularly bring them uncomfortably close to Earth. An asteroid just 140 meters across, smaller than 2 football fields, could destroy a major city. The asteroid that killed the dinosaurs was only about 10 kilometers wide, yet it ended the reign of the most successful animals in Earth's history and triggered a mass extinction that lasted for millions of years. Objects this size or larger cross Earth's orbit regularly. We've discovered that space itself is expanding, driven by a mysterious force called dark energy that makes up 68% of the universe. We don't understand what dark energy is or what it might do to the fundamental structure of reality. The atoms that make up your body, the planet beneath your feet, even the stars in the sky, represent less than 5% of the universe. The rest is dark matter and dark energy, invisible, unknown, and potentially devastating forces that we're only beginning to comprehend. Even our position in the galaxy puts us at risk. We're located about halfway out from the galactic center in what's called the galactic habitable zone. But this zone isn't static. As our solar system orbits the galaxy every 230 million years, we periodically pass through the galaxy's spiral arms, regions with higher concentrations of massive stars, more frequent supernovas, and elevated levels of cosmic radiation. Every 62 million years or so, our solar system also bobs up and down through the galactic plane, exposing us to different cosmic radiation environments. Some scientists have linked these galactic oscillations to mass extinction events in Earth's history, suggesting that our position in space directly influences the survival of life on our planet. The connection between space and Earth isn't theoretical. It's written in stone, ice, and the fossil record itself. Throughout our planet's history, cosmic events have reached down from the heavens to reshape the very course of evolution, topple civilizations, and remind us that we are never truly safe from the universe's reach. Let's start with the most famous example. The day the dinosaurs died. 66 million years ago, an asteroid roughly 10 kilometers wide, about the size of Manhattan, slammed into what is now Mexico's Yucatan Peninsula at a speed of 20 kilometers per second. The impact created a crater 150 kilometers across and released energy equivalent to 10 billion atomic bombs. But the impact itself was just the beginning of the catastrophe. The collision vaporized rock, creating a cloud of superheated debris that was launched into space before raining back down as molten glass spherules, setting forests ablaze across the globe. The impact triggered magnitude 11 earthquakes, stronger than any earthquake in recorded human history, and tsunamis over 100 meters high that devastated coastlines thousands of kilometers away. The debris cloud blocked out the sun for months, plunging the Earth into what scientists call an impact winter. Photosynthesis stopped, temperatures plummeted, the food chain collapsed from the bottom up. 3/4 of all species on Earth went extinct, including every non-avian dinosaur. The age of reptiles ended in a single day, making way for the age of mammals, and eventually, here's the terrifying part. This wasn't even an unusually large asteroid. Objects this size hit Earth roughly every 100 million years. We're overdue. But cosmic threats don't always announce themselves with Hollywood-style explosions. Sometimes they strike silently, invisibly, with effects that unfold over years or decades. In 1859, the largest recorded solar storm in history provided a preview of how space weather can reach into our daily lives. The Carrington event, named after astronomer Richard Carrington, who observed the solar flare that caused it, sent a massive coronal mass ejection racing toward Earth. When it arrived, the results were both beautiful and terrifying. Auroras appeared as far south as the Caribbean and Hawaii, places where they had never been seen before. The northern lights were so bright that people could read newspapers by their glow. But the electromagnetic pulse also wreaked havoc on the era's cutting-edge technology. The telegraph system. Telegraph wires sparked and caught fire. Telegraph operators received electric shocks. In some areas, the induced currents were so strong that telegraph systems continued operating even after being disconnected from their power sources, running purely on the electricity generated by the magnetic storm. If the Carrington event happened today, the damage would be catastrophic.
2008.
National Academy of Sciences study estimated that a similar solar storm could cause $1 miners, $2 trillion in damage in the United States alone, leaving 130 million people without power for years. Our satellite networks would be crippled, GPS systems would fail, and the internet itself could be severely disrupted. Modern civilization would face a crisis unlike anything in recorded history. The geological record tells us that even more powerful solar storms have hit Earth in the past. Ice core samples from Greenland and Antarctica contain chemical signatures of extreme solar events that occurred in 774 AD and 993 AD. Storms that may have been 10 times more powerful than the Carrington event. Medieval chronicles from these periods describe strange lights in the sky and unusual atmospheric phenomena. But the full scale of these cosmic assaults only became clear when scientists learned to read the story written in ancient ice. More recently, we've experienced cosmic wake-up calls that demonstrate our vulnerability. In 1989, a relatively modest solar storm knocked out the power grid in Quebec, leaving 6 million people without electricity for 9 hours and causing millions of dollars in damage. The aurora from this storm was visible as far south as Texas. In 2012, Earth narrowly missed what could have been the most devastating solar storm in modern history. A massive coronal mass ejection tore through Earth's orbit, exactly where our planet had been just 1 week earlier. If the timing had been different, the consequences could have sent human civilization back decades. If the Tunguska event of 1908 showed us how even a relatively small cosmic visitor can unleash tremendous destruction. An asteroid or comet fragment, probably only 40 meters across, exploded in the atmosphere over Siberia with the force of 1,000 Hiroshima bombs. The blast flattened 2,000 square kilometers of forest, an area larger than Greater London. The explosion was heard 1,000 kilometers away, and the atmospheric shock wave circled the Earth twice. Imagine if Tunguska had occurred over New York, London, or Tokyo, instead of the sparsely populated Siberian wilderness. The death toll would have been catastrophic, and we would have had no warning whatsoever. Objects this size hit Earth approximately once every 300 years, and we've identified only a tiny fraction of them. Even smaller cosmic visitors regularly remind us of our vulnerability. In 2013, an asteroid only 17 meters across exploded over Chelyabinsk, Russia, with the force of 30 Hiroshima bombs. The blast wave damaged thousands of buildings and injured over 1,500 people. Security cameras across the region captured the terrifying moment when a routine morning was shattered by a flash brighter than the sun, followed by a shockwave that turned windows into deadly shrapnel. The Chelyabinsk meteor was completely undetected before it struck. Our most sophisticated early warning systems, designed to spot dangerous asteroids, completely missed an object that injured 1,500 people. It approached from the direction of the sun, hiding in our blind spot until the moment of impact. These historical events aren't ancient history. They're previews of our future. Every impact crater on Earth, every ice core record of ancient solar storms, every fossil bed marking a mass extinction, is evidence that cosmic forces regularly reach down from space to alter the course of life on our planet. The question isn't whether it will happen again. The question is when and whether we'll be ready. During the height of the Cold War, American military satellites designed to detect secret nuclear weapons tests began picking up mysterious flashes of gamma radiation from space. These weren't the signatures of Soviet bombs. They were something far more terrifying. The year was 1967, and the Vela satellites, orbiting high above Earth, were humanity's watchdogs against nuclear proliferation. Their mission was straightforward: detect a telltale gamma-ray signature of nuclear explosions anywhere on or around Earth. What they found instead would fundamentally change our understanding of the universe and reveal the existence of the most powerful weapons in the cosmos. The first detection was brief. Just a few seconds of intense gamma radiation coming not from Earth, but from deep space. Then another and another. These cosmic flashes were unlike anything scientists had ever seen. They lasted anywhere from milliseconds to several minutes, released more energy in seconds than our sun produces in its entire lifetime, and they seemed to come from random directions across the sky. For years, these detections remained classified military secrets. The US government wasn't about to reveal the capabilities of their nuclear detection satellites, even to announce one of the most important astronomical discoveries in history. It wasn't until 1973 that the existence of gamma-ray bursts was finally revealed to the scientific community, launching a decades-long mystery that would challenge everything we thought we knew about stellar death and cosmic violence. The early observations raised more questions than they answered. These gamma-ray bursts, or GRBs, were clearly astronomical in origin. No human technology could produce such intense, brief flashes of gamma radiation, but their random distribution across the sky was puzzling. If they came from within our galaxy, scientists expected to see them concentrated along the plane of the Milky Way, where most of our galaxy's stars reside. Instead, they appeared to come from every direction equally. This led to two competing theories that divided the astronomical community for decades. Some scientists argued that GRBs were relatively nearby events within our own galaxy, perhaps neutron stars, experiencing violent magnetic field reconnections, or comets falling into compact objects. Others proposed something far more exotic, that these bursts came from the distant universe, making them the most energetic events since the Big Bang itself. The debate raged through the 1980s and 1990s as more sophisticated satellites detected hundreds of these cosmic flashes. Each new observation added pieces to the puzzle, but the picture remained frustratingly incomplete. The bursts were too brief to study in detail, and by the time ground-based telescopes could be pointed at their locations, any visible afterglow had usually faded beyond detection. The breakthrough came in 1997 with the Italian-Dutch satellite Bepi, which could not only detect gamma-ray bursts, but also quickly determine their precise locations and alert ground-based observatories within hours. On February 28, 1997, Bepi detected GRB 970228 and immediately transmitted its coordinates to astronomers around the world. For the first time in the 30-year history of gamma-ray burst research, telescopes could observe the aftermath of one of these cosmic explosions. What they found was revolutionary, a fading optical counterpart in a distant galaxy, billions of light-years away. This single observation resolved the decades-long debate and revealed the true nature of gamma-ray bursts. They weren't local events in our cosmic backyard. They were the death screams of massive stars in distant galaxies. Explosions so powerful that they could be seen across the entire observable universe. The energy released in a typical gamma-ray burst exceeds the total energy output of our Sun over its entire 10 billion-year lifetime, concentrated into mere seconds. The implications were staggering. If gamma-ray bursts could be detected from billions of light-years away, what would happen if one occurred in our own galaxy? Computer models suggested that a nearby GRB could strip away Earth's ozone layer, expose the planet's surface to lethal ultraviolet radiation, and trigger a mass extinction event that could end complex life on our planet. As more observations poured in, the picture became both clearer and more terrifying. Gamma-ray bursts appeared to be associated with the collapse of the most massive stars in the universe, stars so large that when they die, they don't just explode as ordinary supernovas. Instead, they form black holes while simultaneously launching jets of material at nearly the speed of light, jets that focus their energy into narrow beams of destruction. The discovery of gamma-ray bursts forced scientists to confront an uncomfortable truth. The universe is far more violent and dangerous than we had ever imagined. These cosmic weapons can strike without warning, their light-speed gamma rays providing no advance notice of their arrival. By the time we detect a gamma-ray burst, we're already bathed in its radiation. Today, satellites like NASA's Swift and Fermi detect gamma-ray bursts almost daily, each one representing the violent death of a massive star somewhere in the universe. Every detection reminds us that we live in a cosmos where stellar explosions routinely release more energy than entire galaxies, where the death of a single star can potentially sterilize planets hundreds of light-years away. The Cold War satellites that first detected these cosmic monsters were looking for evidence of human weapons. Instead, they discovered that nature has already built the ultimate weapons of mass destruction, and they're firing constantly throughout the universe. To understand the true horror of a gamma-ray burst, you need to imagine the most extreme physics possible, conditions so violent that they break the normal rules of space and time, creating weapons that can kill across galactic distances. It begins with a star so massive that our Sun would be like a grain of sand compared to a mountain. These stellar monsters contain 20, 50, even 100 times more matter than our Sun, all packed into a sphere that might be only twice as large. For millions of years, these giants have been fighting a losing battle against their own gravity, burning heavier and heavier elements in their cores to generate the pressure needed to avoid collapse. But every star has a breaking point, and for the most massive stars, that breaking point creates the most violent events in the known universe. The final stages happen terrifyingly fast. A star's core, now composed primarily of iron, can no longer sustain fusion reactions. Iron nuclei cannot be fused to release energy. They can only absorb it. In less than a second, the stellar core, which has been supporting the star's immense weight for millions of years, simply vanishes. The inner core collapses from the size of Earth to the size of Manhattan, in a quarter of a second. What happens next defies human comprehension. The collapsing matter becomes so dense that protons and electrons are crushed together to form neutrons. A teaspoon of this neutron-degenerate matter would weigh as much as Mount Everest. The gravity becomes so intense that it warps space and time itself, creating a black hole with an appetite that can never be satisfied. But the collapse doesn't happen uniformly, and this asymmetry is what makes gamma-ray bursts so terrifyingly powerful. As the core collapses and forms a black hole, conservation of angular momentum causes it to spin faster and faster, like a figure skater pulling in their arms. Magnetic field lines, trapped in the collapsing plasma, become twisted and amplified to strengths trillions of times more powerful than Earth's magnetic field. The combination of the rapidly spinning black hole and these impossibly strong magnetic fields creates what astrophysicists call a magnetorotational explosion, a cosmic particle accelerator that focuses the star's death energy into two narrow jets of material, moving at 99.9%, the speed of light. These jets bore through the dying star like cosmic drill bits, channeling temperatures of over 10 billion degrees and magnetic field strengths that would instantly vaporize any known material. As they break free from the star's surface, they create a focused beam of gamma radiation, so intense that it can outshine entire galaxies for seconds or minutes. The physics involved is so extreme that it challenges our understanding of matter and energy. The jets accelerate electrons to energies millions of times higher than anything we can create in our most powerful particle accelerators. These ultra-relativistic particles then interact with magnetic fields and photons to produce gamma rays with energies exceeding 100 billion electron volts. Radiation so energetic that each individual photon carries enough energy to power a household light bulb for several seconds. What makes gamma-ray bursts uniquely terrifying is their geometry. Unlike a supernova, which spreads its energy in all directions, a gamma-ray burst focuses its power into jets with opening angles of just a few degrees. This means that if you're unlucky enough to be in the direct path of a GRB jet, you receive not just a share of the star's death energy, but a concentrated beam containing as much power as hundreds of supernovas combined. The jets themselves are marvels of extreme physics. They contain material moving so close to the speed of light that relativistic effects become dominant. Time dilation means that processes that would normally take hours happen in minutes from our perspective. Length contraction compresses the jet material into impossibly thin sheets of matter. The Doppler effect shifts the jet's radiation to higher and higher energies as it accelerates toward us. As the jet travels through space, it sweeps up interstellar material, creating shock waves that generate additional radiation across the electromagnetic spectrum. This creates the afterglow that can be observed for weeks or months after the initial gamma-ray burst, providing scientists with crucial information about the explosion and its environment. But perhaps the most unsettling aspect of gamma-ray bursts is their efficiency at converting matter into pure energy. Einstein's famous equation E=mc² tells us that mass and energy are interchangeable, but most nuclear reactions convert only a tiny fraction of matter into energy. Nuclear fusion, the process that powers stars, converts less than 1% of the mass involved into energy. Even nuclear fission, the most efficient process available to human technology, converts less than 0.1% of mass into energy. Gamma-ray bursts are different. They can convert up to 40% of the collapsing star's mass into pure energy, channeled into those devastating jets. This makes them the most efficient energy conversion process known in the universe, more efficient than anything physics says should be possible outside of matter-antimatter annihilation. The energy scales involved are almost impossible to comprehend. A typical gamma-ray burst releases more energy in 10 seconds than our sun will produce over its entire 10 billion year lifetime. The most powerful GRBs release more energy than our sun would produce if it burned for 100 billion years, longer than the current age of the universe. To put this in perspective, If you could somehow capture just 1 second of energy from a gamma-ray burst occurring 100 light-years away, it would be enough to supply all of Earth's energy needs for the next billion years. But that same energy, uncontrolled and focused into a beam of destruction, could sterilize our planet's surface and end complex life as we know it. The jets from gamma-ray bursts move so fast and carry so much energy that they actually outrun their own light, creating what physicists call superluminal motion. To observers watching from the side, the jets appear to move faster than light itself. Though this is an illusion created by the extreme geometry and relativistic speeds involved. When these jets finally run out of energy and begin to slow down, they've typically traveled thousands of light-years from their source, leaving a trail of destruction that spans interstellar distances. Any planets, moons, or spacefaring civilizations unlucky enough to lie in their path would be subjected to radiation doses millions of times higher than what it would take to sterilize a world. This is the anatomy of annihilation, the conversion of stellar death into cosmic weapons that can kill across vast distances, turning the universe itself into a battlefield where the deaths of distant stars can reach across space and time to end civilizations they will never know existed. The cosmic kill zone around a gamma-ray burst isn't measured in miles or even thousands of miles. It's measured in light-years, creating spheres of destruction that can encompass hundreds of star systems and potentially sterilize entire regions of the galaxy. When astrophysicists first calculated the lethal range of a gamma-ray burst, the results were sobering enough to fundamentally change how we think about the long-term survival of complex life in the universe. A GRB, occurring within 8,000 light-years of Earth, a distance that seems vast but represents just our immediate galactic neighborhood, could deliver enough radiation to our planet to trigger a mass extinction event. But the true horror of gamma-ray bursts isn't just their range, it's how they kill. Unlike the quick, dramatic destruction of an asteroid impact, GRBs inflict death through an insidious process that unfolds over months and years, systematically dismantling the very foundations of life. The gamma rays themselves arrive first, traveling at the speed of light. These high-energy photons slam into Earth's upper atmosphere, where they interact with nitrogen and oxygen molecules to create a cascade of chemical reactions. The most critical reaction produces nitrogen oxides, compounds that normally exist in trace amounts but are suddenly generated in massive quantities. These nitrogen oxides become atmospheric poison, catalytically destroying ozone molecules in a chain reaction that can deplete up to 75% of Earth's protective ozone layer within weeks. Without this crucial shield, the sun's ultraviolet radiation, normally filtered out harmlessly, begins reaching Earth's surface at levels that are immediately lethal to most life forms. The effects cascade through the biosphere with devastating efficiency. Phytoplankton, the microscopic organisms that form the base of oceanic food chains and produce much of our planet's oxygen, begin dying en masse as UV radiation penetrates the ocean's surface layers. On land, plants suffer severe cellular damage, with many species simply unable to survive the increased radiation levels. Seki bidevor Buddha naive. But the atmospheric destruction doesn't stop with ozone depletion. The same chemical reactions that destroy ozone also produce other reactive compounds that create a brown, smoggy haze throughout the stratosphere. This haze blocks visible light from reaching Earth's surface, creating a cosmic winter effect similar to nuclear winter. Temperatures drop, photosynthesis becomes impossible, and the planet plunges into an extended period of darkness and cold. Computer models suggest that this combination of increased UV radiation and reduced sunlight could persist for up to 5 years after a nearby gamma-ray burst. For complex ecosystems dependent on stable environmental conditions, this represents an extinction-level catastrophe that few species could survive. The kill zone isn't uniform. It depends entirely on a planet's position relative to the GRB's focused jets. If Earth were positioned directly in line with a gamma-ray burst jet, even a GRB occurring 50,000 light-years away could deliver lethal radiation doses. The focused nature of these cosmic weapons means that while they might sterilize planets in one direction, star systems just a few degrees off-axis might experience no effects at all. This geometry creates a chilling scenario. Gamma-ray bursts could be responsible for creating vast dead zones in galaxies where complex life simply cannot evolve or survive long-term. Some scientists have proposed that GRBs might be one solution to the Fermi paradox, the puzzling absence of detectable alien civilizations. Perhaps advanced life is rare, not because planets suitable for life are uncommon, but because gamma-ray bursts regularly sterilize large regions of galaxies before complex civilizations can develop. The timing of GRBs relative to planetary evolution is crucial. A gamma-ray burst that occurred 4 billion years ago might have delayed the emergence of complex life on Earth by hundreds of millions of years. If one occurred 500 million years ago, during the Cambrian explosion when complex life was first diversifying rapidly, it could have ended that diversification and prevented the evolution of vertebrates entirely. Even more disturbing is the realization that the kill zone extends beyond just the initial gamma-ray pulse. The high-energy particles and cosmic rays generated by the GRB continue to bombard nearby star systems for thousands of years after the initial event. This extended radiation exposure could prevent the recovery of complex ecosystems, creating sterile zones that persist for geological timescales. Recent observations have revealed that gamma-ray bursts may be even more deadly than initially calculated. Some GRBs produce precursor emissions and extended emissions that can deliver additional radiation doses over periods of hours or days. Others generate ultra-high energy cosmic rays that can penetrate planetary atmospheres and magnetospheres, reaching the surface even on worlds with strong magnetic fields. Within this cosmic kill zone, the universe becomes a fundamentally hostile place for complex life, where the violent deaths of distant stars can reach across space to reset evolution and ensure that intelligence, if it arises at all, remains rare and fragile. Right now, scattered throughout our galactic neighborhood, there are stellar time bombs ticking toward detonation, massive stars that will eventually collapse into black holes and potentially fire gamma-ray bursts directly at Earth. The terrifying reality is that we can identify these cosmic weapons, but we have no idea when they'll fire or where they'll aim. Astronomers have catalogued dozens of potential gamma-ray burst candidates within the danger zone around Earth, and each one represents a loaded chamber in our cosmic game of Russian roulette. These aren't distant theoretical threats. They're our stellar neighbors, close enough that when they die, they could fundamentally alter the course of life on our planet. The most notorious candidate is Eta Carinae, a stellar monster located just 7,500 light-years away in the southern constellation Carinae. This hypergiant star contains over 100 times the mass of our Sun, making it one of the most massive stars known in our galaxy. Eta Carinae is so unstable that it's already experienced massive eruptions in the 1840s. It briefly became the second brightest star in Earth's sky, as it ejected material equivalent to several solar masses in what astronomers call the Great Eruption. What makes Eta Carinae particularly menacing is its rapid rotation. Computer models suggest that when this stellar giant finally collapses, its spin rate will be fast enough to generate the focused jets characteristic of long-duration gamma-ray bursts. Worse yet, observations indicate that Eta Carinae's rotation axis may be pointed roughly in Earth's direction. If it explodes as a GRB within the next million years, a blink of an eye in cosmic terms, we could be looking directly down the barrel of one of the universe's most powerful weapons. But Eta Carinae isn't alone in threatening our planet. Cho 104, a Wolf-Rayet star, located 8,000 light-years away in the constellation Sagittarius, presents another chilling possibility. Wolf-Rayet stars are in the final stages of stellar evolution, having already blown away their outer layers to reveal the hot, dense cores beneath. These stellar cores are burning through their remaining fuel at an accelerated rate, racing toward gravitational collapse and potential GRB formation. What makes WR104 particularly concerning is its unique structure. This isn't a single star, but a binary system where two massive stars orbit each other so closely that they share material in a cosmic dance of mutual destruction. The interaction between these stars has created a spectacular pinwheel nebula of ejected material, and the geometry of this system suggests that when the primary star collapses, any resulting gamma-ray burst could be aimed directly at our solar system. Recent observations have revealed that WR104's rotation axis appears to be tilted at an angle that could place Earth within the cone of destruction when the star finally explodes. The uncertainty in these measurements means we can't be certain of our safety. We're essentially gambling with the survival of our species, based on the precise orientation of a dying star, thousands of light years away. Closer to home, we have Ik Pegasi, located just 150 light-years from Earth, practically next door in galactic terms. This white dwarf star in a binary system is slowly accumulating material from its companion star, approaching the critical mass limit where it will explode as a Type Ia supernova. While not a gamma-ray burst candidate itself, Ik Pegasi represents the closest potential supernova to Earth, and its explosion could still deliver dangerous levels of radiation to our planet. Perhaps most unsettling of all is our growing realization that gamma-ray burst candidates might be far more common than we initially thought. Recent surveys have identified numerous massive stars in our galactic vicinity that show signs of rapid rotation and the heavy element compositions associated with GRB progenitors. Wabexbenu Chenier, stars like WR142, Zeta Puppis, and P Cygni all exhibit characteristics that place them on the potential GRB watch list. The Wolf-Rayet star WR25, located in the Carina Nebula alongside Eta Carinae, adds another loaded chamber to our cosmic revolver. This star shows evidence of rapid mass loss and instability, suggesting it's approaching the end of its stellar life. If both WR25 and Eta Carinae were to explode as gamma-ray bursts within a relatively short time period, the combined radiation assault could be more devastating than either event alone. Even more disturbing is the discovery of stealth GRB candidates, massive stars that appear relatively stable from Earth, but may be undergoing rapid changes that we can't easily observe. The three-dimensional structure of our galaxy means that many potential threats may be hidden behind dust clouds or positioned at angles that make their properties difficult to determine. Advanced computer simulations suggest that our galaxy experiences a potentially dangerous gamma-ray burst roughly every 100,000 to 1 million years. Given that complex life has existed on Earth for approximately 500 million years, we've likely already survived several nearby GRBs, events that may be recorded in the fossil record as unexplained mass extinction events. The most chilling aspect of our galactic Russian roulette is the complete unpredictability of when these stellar weapons will fire. Massive stars can remain stable for millions of years before collapsing in a matter of seconds. Eta Carinae might explode tomorrow, or it might continue burning for another 100,000 years. We simply don't know. What we do know is that the chamber is loaded, the cosmic revolver is spinning, and somewhere in our galactic neighborhood, the trigger is being pulled on weapons that could reset the story of life on Earth. We're not just passive observers of this cosmic game, we're the target. Every morning we wake to the gentle warmth of our local star, never suspecting that the same sun that makes life possible is also capable of unleashing forces that could end our technological civilization in a matter of hours. We think of the sun as stable, predictable, benign, a steady source of light and heat that has faithfully illuminated Earth for billions of years. This perception shapes everything from our daily routines to our long-term planning. We schedule space missions, launch satellites, and build power grids, all based on the assumption that our star will continue its reliable performance indefinitely. But the sun, we think we know, is only half the story. Hidden beneath that familiar bright disk is a seething cauldron of magnetic chaos, where invisible force fields, hundreds of times stronger than Earth's magnetic field, twist and writhe through plasma heated to millions of degrees. These magnetic field lines, constantly generated by the sun's rotation and convection, don't just stay quietly confined to the solar surface. They regularly explode outward with devastating force. The sun's magnetic field is nothing like Earth's relatively simple, stable dipole field. Instead, it's a complex, dynamic system that changes dramatically over an 11-year cycle. During solar maximum, the peak of this cycle, the sun's magnetic field becomes so tangled and unstable that it regularly snaps like overstretched rubber bands, releasing magnetic energy equivalent to billions of atomic bombs in single events. These magnetic field reconnection events manifest as solar flares, brief, intense explosions of electromagnetic radiation that can increase the sun's brightness by orders of magnitude in specific wavelengths. But solar flares are just the opening act. The real threat comes from coronal mass ejections, or CMEs, billion-ton clouds of magnetized plasma hurled into space at speeds that can exceed 3,000 kilometers per second. Imagine a magnetic bubble the size of Jupiter, filled with plasma heated to 20 million degrees Celsius, racing toward Earth at 1% the speed of light. That's what a major coronal mass ejection looks like, and our sun launches these weapons of mass disruption regularly, especially during periods of high magnetic activity. What makes CMEs particularly dangerous is their magnetic cargo. These plasma clouds carry with them twisted, concentrated magnetic fields that can interact catastrophically with Earth's magnetosphere. When a CME with the right magnetic orientation hits our planet, it can cause what scientists call magnetic reconnection, a process that transfers enormous amounts of energy directly into Earth's magnetic field system. The effects cascade through our planet's magnetic environment like a cosmic tsunami. The magnetosphere, normally a protective shield, becomes a conduit for destruction. Energetic particles are accelerated to tremendous speeds and funneled down magnetic field lines toward Earth's poles. The entire magnetosphere can be compressed and distorted, sometimes allowing the solar wind to reach much deeper into our planetary environment than normal. But here's what makes modern solar storms uniquely terrifying. Our technology has evolved to become exquisitely sensitive to the very forces that CMEs unleash. The same electromagnetic effects that created beautiful auroras for our ancestors now threaten to destroy the technological infrastructure that defines modern civilization. Our power grids, designed for predictable terrestrial electrical loads, can be overwhelmed by the massive induced currents generated when CMEs interact with Earth's magnetic field. Transformers, the critical components that regulate electrical distribution, can be permanently damaged by these geomagnetically induced currents, taking months or years to replace. Our satellite networks, positioned in space for optimal communication coverage, sit directly in the path of CME impacts. The energetic particles can damage sensitive electronics, disrupt communications, and even knock satellites completely out of their orbits. GPS systems, which depend on precise timing signals from orbital satellites, can become completely unreliable during major space weather events. Perhaps most unsettling is the realization that our sun's quiet periods may be more dangerous than its active ones. Historical records suggest that the sun can experience grand minima, decades-long periods of reduced activity, that can actually make the solar wind more dangerous by allowing high-energy cosmic rays to penetrate deeper into the solar system. The Maunder minimum, a period of extremely low solar activity from 1645 to 1715, coincided with the coldest part of the Little Ice Age. But recent research suggests that these quiet periods might also increase our vulnerability to the most dangerous type of space weather, fast-moving CMEs that can reach Earth in less than 18 hours, giving us virtually no time to prepare. Our technological civilization has grown up during a period of relatively moderate solar activity. We've never experienced what the sun is truly capable of unleashing, and when that day comes, we may discover that our greatest threat comes not from the depths of space, but from the star that gives us life itself. September 1st, 1859, began as an ordinary Thursday morning for Richard Carrington, a wealthy English astronomer who had turned his private observatory into one of the world's premier solar observation stations. As he focused his telescope on the sun's surface, tracking the dark sunspots that drifted across our star's bright disk, he had no idea he was about to witness the most powerful solar storm in recorded human history. At 11:18 a.m., something unprecedented happened. Two brilliant white lights erupted from a cluster of sunspots, blazing so intensely that they were visible against the sun's surface, a phenomenon that should have been impossible to observe with the solar observation techniques of the era. Carrington watched in amazement as these white light flares danced across the solar surface for about 5 minutes before fading away. 17 hours later, the consequences of what Carrington had witnessed began reaching Earth in the form of a coronal mass ejection, so powerful that it would redefine humanity's understanding of space weather and our vulnerability to cosmic forces. The first sign that something was wrong came from the telegraph systems that had recently connected cities across North America and Europe. Telegraph operators reported that their lines were carrying electrical currents so strong that the wires were sparking and catching fire. A fire can you series of government. In Boston, a telegraph operator received an electric shock so severe that he was knocked unconscious. Telegraph offices from Maine to London reported that their equipment was behaving as if possessed by some malevolent electrical spirit. But this was just the beginning of the technological chaos. Telegraph systems throughout the eastern United States began operating without any connection to their power sources, running purely on the electrical currents induced by the magnetic storm raging in Earth's upper atmosphere. Some operators discovered they could disconnect their batteries entirely and still send messages across vast distances using only the electricity generated by the space weather event. The visual effects were even more spectacular and terrifying. Auroras, normally confined to the polar regions, appeared as far south as Rome, Havana, and the Caribbean. In New York City, people gathered on rooftops to watch the northern lights dance across the Manhattan sky. The auroras were so bright that people throughout the northeastern United States could read newspapers by its glow at midnight. Gold miners in the Rocky Mountains woke up thinking it was dawn and began preparing breakfast, completely disoriented by the brilliant red and green lights filling the pre-dawn sky. Birds began chirping and roosters crowed, confused by the artificial daylight created by the electromagnetic storm. Witnesses described the aurora as supernatural fires dancing across the heavens. In some areas, the lights appeared as massive crimson curtains hanging from the sky. In others, they formed spiral patterns that seemed to pulse with an otherworldly heartbeat. Many people, having never seen auroras before, thought they were witnessing the end of the world. Telegraph operator accounts from that night read like descriptions of a technological apocalypse. In Washington, D.C., a telegraph operator reported that streams of fire were coming from the telegraph lines. In France, Napoleon III's government lost all telegraphic communication with its outlying provinces. The newly laid transatlantic telegraph cable, one of the greatest technological achievements of the era, was completely disrupted. But perhaps the most unnerving reports came from the compasses. Magnetic compasses throughout the northern hemisphere began spinning wildly or pointing in completely wrong directions. Ships at sea found themselves unable to navigate reliably, their magnetic compasses rendered useless by the invisible forces, unleashing chaos in Earth's magnetic field. What made the Carrington event particularly terrifying was its global reach. This wasn't a localized phenomenon affecting one region or country. It was a planetary event that demonstrated humanity's complete vulnerability to forces beyond our control or understanding. Telegraph systems failed simultaneously across multiple continents. Auroras appeared in both the northern and southern hemispheres. The magnetic disturbance was recorded by instruments from London to Bombay. Scientists later calculated that the coronal mass ejection responsible for the Carrington event traveled from the Sun to Earth in just 17 hours, extraordinarily fast, even by modern standards. Most CMEs take 2 to 4 days to make the journey, but this cosmic bullet reached Earth at speeds exceeding 2,000 kilometers per second. giving human civilization virtually no warning of the impending technological catastrophe. The intensity of the magnetic storm was beyond anything in the modern scientific record. Ground-based magnetometers, instruments designed to measure variations in Earth's magnetic field, were driven completely off-scale. The induced electrical currents were so strong that they not only disrupted telegraph operations, but actually enhanced the performance of some systems, allowing messages to be sent over longer distances than normally possible. What makes the Carrington event even more sobering is that it occurred during what scientists now recognize as a relatively moderate period of solar activity. The 1859 event wasn't the product of an unusually active solar cycle. It was just an exceptionally powerful individual storm during a fairly typical solar maximum period. Contemporary accounts suggest that, if not for the limited electrical infrastructure of the mid-19th century, the damage could have been catastrophic. The telegraph represented the cutting edge of electrical technology in 1859, but it was primitive compared to the complex, interconnected power grids and electronic systems that define modern civilization. Ice core samples from Greenland and Antarctica preserve a chemical record of the Carrington event, showing spikes in nitrates and other compounds produced when energetic particles from the solar storm interacted with Earth's atmosphere. These same ice cores reveal that even more powerful solar storms have struck Earth in the past, including events in 774 AD and 993 AD that may have been significantly more intense than the Carrington event. The 1859 storm also provided the first clear evidence that the aurora borealis and aurora australis were directly connected to solar activity. Before Carrington's observations, many scientists believed auroras were purely atmospheric phenomena, unrelated to events on the sun. The correlation between the solar flare Carrington observed and the global aurora that followed 17 hours later established the connection between solar storms and geomagnetic disturbances. Perhaps most importantly, the Carrington event gave humanity its first glimpse of what modern scientists call space weather, the realization that conditions in space can directly affect life and technology on Earth. It shattered the illusion that our planet exists in a calm, stable cosmic environment and revealed that we are intimately connected to the violent processes occurring on our local star. The fire that fell from the sky in 1859 was a warning, a preview of what our increasingly electronic civilization will face when the next great solar storm strikes. If the Carrington event happened today, it wouldn't just disrupt telegraph lines, it would collapse the technological foundation of modern civilization, potentially sending billions of people back to a pre-industrial way of life within hours. The terrifying reality is that our technology has evolved to become exquisitely vulnerable to the very forces that solar storms unleash. Every advancement that has made our lives more connected, more efficient, and more dependent on electronic systems has also made us more susceptible to space weather disasters. Consider our electrical power grid, the invisible nervous system that powers everything from hospitals to data centers to the pumps that deliver water to our homes. Modern power grids are marvels of engineering, designed to efficiently distribute electricity across vast distances using high-voltage transmission lines and sophisticated transformer networks. But these same characteristics that make them efficient also make them perfect antennas for capturing the geomagnetically induced currents generated by solar storms. When a coronal mass ejection hits Earth's magnetosphere, it creates rapid changes in the planet's magnetic field. These changing magnetic fields induce electrical currents in any long conductor. Power lines stretching for hundreds of miles are among the longest conductors on Earth. During the 1989 Quebec blackout, a relatively modest solar storm induced currents strong enough to trip protective systems and shut down the entire provincial power grid, leaving 6 million people without electricity. But losing power for a few hours is the least of our concerns. The real nightmare scenario involves permanent damage to the massive power transformers that regulate electrical distribution. These transformers, some weighing hundreds of tons, are custom-built components that can take months or years to replace. They're also designed to handle specific electrical loads, not the chaotic, high-amplitude currents that solar storms can induce. A study by the National Academy of Sciences estimated that a Carrington-level solar storm today could damage or destroy hundreds of these critical transformers across North America. With limited replacement capacity and complex installation requirements, repairs could take years to complete, leaving vast regions without reliable electricity for extended periods. The cascading effects would be catastrophic. Modern water treatment plants depend on electricity to operate pumps and filtration systems. Without power, most cities would run out of clean water within days. Food distribution networks, dependent on refrigeration and electronic inventory systems, would collapse. Gas stations couldn't pump fuel. Hospitals would be forced to rely on emergency generators with limited fuel supplies, and telecommunications networks would gradually fail as backup batteries died. Our satellite infrastructure represents another critical vulnerability. More than 4,000 active satellites orbit Earth, providing everything from GPS navigation to weather forecasting to international communications. These satellites operate in the harshest environment imaginable, constantly bombarded by radiation and exposed to the full fury of space weather. During major solar storms, the number of energetic particles in space can increase by factors of thousands or tens of thousands. These particles can penetrate satellite shielding, causing electronic components to malfunction or fail permanently. Solar storms can also heat Earth's upper atmosphere, causing it to expand and create increased drag on low-orbit satellites, potentially pulling them out of their intended orbits. The GPS system, which most people think of as a convenience for navigation, has actually become critical infrastructure for modern society. GPS timing signals synchronize everything from financial trading networks to cellular phone systems to power grid operations. Many systems have no backup timekeeping capability. If GPS fails, they simply stop working properly. The Internet itself, often described as a decentralized network designed to survive disasters, actually depends on a surprisingly fragile infrastructure of undersea cables, satellite links, and ground-based routing stations. Solar storms can disrupt satellite communications, interfere with radio transmissions, and cause cascading failures in routing systems that could fragment the global internet for days or weeks. Perhaps most concerning is our complete dependence on just-in-time delivery systems for everything from food to medicine to critical spare parts. Modern supply chains are optimized for efficiency, not resilience. Most cities have only a few days' worth of food in their stores and warehouses. Hospitals typically maintain small inventories of critical supplies, depending on regular deliveries to restock. If transportation and communication systems fail simultaneously, these supply chains could collapse rapidly. Our financial systems present another catastrophic vulnerability. Modern banking depends entirely on electronic transactions and communications. ATMs, credit card systems, stock markets, and international wire transfers could all be disrupted by a major solar storm. Even if the physical infrastructure remained intact, the loss of GPS timing signals and communication satellites could make it impossible to process transactions or verify account balances. Modern banking things feri and retray the abajasolientes. The Lloyd's of London insurance market has identified solar storms as one of the top emerging risks facing the global economy, with potential damages from a major event estimated at 60 cents to $2.6 trillion in the United States alone. But these figures only account for direct economic losses. They don't capture the potential human cost of widespread infrastructure failure. Emergency management agencies have begun developing response plans for extreme space weather events, but the scale of the potential disaster dwarfs conventional emergency planning. How do you evacuate a city when the traffic control systems don't work? How do you coordinate disaster response when communications networks are down? How do you provide emergency medical care when hospitals have no power and no way to obtain supplies? The most sobering realization is that we've never actually tested our modern technological infrastructure against a truly severe solar storm. The most powerful space weather events of the satellite era have been relatively modest compared to historical storms like the Carrington event. We're conducting a vast, uncontrolled experiment with the technological foundation of human civilization, and we won't know the results until the next great solar storm strikes. 66 million years ago, on what seemed like an ordinary day in the late Cretaceous period, a mountain-sized piece of rock and metal, traveling at 20 kilometers per second, struck the Yucatan Peninsula with the force of 10 billion atomic bombs. In that single moment of cosmic violence, the age of dinosaurs ended and the age of mammals began. The asteroid that changed the course of Earth's history was perhaps 10 kilometers across, roughly the size of Manhattan. It had been traveling through space for millions of years, a dark wanderer in the cosmic void, following an orbit that would eventually intersect with a small blue planet where giant reptiles ruled vast continents. The dinosaurs, masters of their world for over 160 million years, had no idea that their extinction was hurtling toward them at 72,000 kilometers per hour. When the asteroid entered Earth's atmosphere, it compressed the air in front of it so violently that the atmosphere itself became a plasma hotter than the sun's surface. North, the friction generated by its passage vaporized the incoming object's outer layers, creating a brilliant fireball that lit up the sky brighter than 1,000 suns. But unlike meteors that burn up harmlessly in the atmosphere, this cosmic mountain was too large to be stopped by air resistance. The impact itself lasted only seconds, but those seconds rewrote the rules of life on Earth. The asteroid struck what is now the Yucatan Peninsula, with an energy release equivalent to 100 trillion tons of TNT, roughly 2 million times more powerful than the largest nuclear weapon ever detonated. The collision created a crater 150 kilometers across and 20 kilometers deep, vaporizing not just the asteroid, but cubic kilometers of Earth's crust. The immediate effects were apocalyptic. The impact generated seismic waves equivalent to a magnitude 11 earthquake, stronger than any earthquake in recorded human history. These shock waves traveled around the globe multiple times, triggering volcanic eruptions, landslides, and massive tsunamis. Trees were flattened thousands of kilometers from the impact site, and the ground shook violently from Mexico to Montana. But the truly devastating effects were just beginning. The impact vaporized thousands of cubic kilometers of rock, launching it high into the atmosphere as a mixture of molten droplets and superheated gas. Much of this material was ejected with such force that it escaped Earth's atmosphere entirely, traveling into space before falling back to Earth as a global shower of molten glass spherules. As this debris rained back down across the planet, it heated the atmosphere to temperatures that turned the sky into a giant oven. Forests spontaneously ignited across entire continents. The returning ejecta was so hot that it may have raised global air temperatures to over 300 degrees Celsius for several hours. Any animal caught in the open would have been literally cooked alive. The impact also vaporized massive amounts of sulfur-rich rock, launching billions of tons of sulfur compounds into the stratosphere. These compounds formed aerosol particles that reflected sunlight back into space, beginning a rapid cooling phase that followed the initial period of extreme heating. Within days, global temperatures plummeted as the sun was obscured by a thick haze of impact debris and sulfur aerosols. This impact winter persisted for months or possibly years. Photosynthesis virtually stopped as sunlight levels dropped to less than 1% of normal. Plants died en masse, and the collapse of primary productivity cascaded up through the food chain with devastating efficiency. Herbivorous dinosaurs, many of which required hundreds of pounds of plant matter daily, began starving within weeks. Carnivorous dinosaurs followed as their prey disappeared. The chemical signature of this catastrophe is preserved in rock layers around the world. A thin band of clay enriched with iridium, an element rare on Earth, but common in asteroids. This KPG boundary layer, as geologists call it, marks one of the most dramatic transitions in Earth's history, separating rock layers filled with dinosaur fossils from those that contain none. But the Chicxulub impact didn't just kill the dinosaurs, it fundamentally reset the trajectory of evolution on Earth. The massive ecological niches left vacant by the extinction of non-avian dinosaurs, created evolutionary opportunities that mammals quickly exploited. Small, adaptable mammalian species that had lived in the shadows of the dinosaurs suddenly found themselves in a world with abundant resources and few large predators. Recent research has revealed that the timing of the impact may have been particularly catastrophic for the dinosaurs. The late Cretaceous period was already a time of environmental stress, with volcanic activity in what is now India releasing massive amounts of greenhouse gases and toxic compounds. The asteroid impact delivered a final blow to ecosystems that were already under severe pressure. The selectivity of the extinction is also telling. Animals that could shelter underground, hibernate, or survive on seeds and detritus had better survival chances than large active animals that required constant food intake. This explains why crocodiles, turtles, and small mammals survived while most dinosaurs perished. The extinction wasn't random. It favored specific survival strategies that happened to be poorly represented among the dominant Cretaceous fauna. Computer simulations of the impact have revealed details that make the catastrophe even more terrifying. The asteroid struck at an angle of about 60 degrees, maximizing the amount of material ejected into the atmosphere. If it had struck head-on, more energy would have been dissipated into the Earth's crust. If it had been a grazing blow, less material would have been vaporized. The angle of impact was nearly optimal for global catastrophe. The discovery of the Chicxulub crater in the 1990s provided the first direct physical evidence of the impact site, confirming what had been a controversial theory since the 1980s. The crater, now buried under younger sediments and largely underwater, shows signs of the enormous forces involved. The rim of the crater was initially pushed up to heights of several kilometers before collapsing back down. The central peak, formed by crustal rebound after the impact, rose to heights of over 1.5 kilometers above the crater floor. Perhaps most sobering is the realization that the Chicxulub impactor wasn't exceptionally large by cosmic standards. Asteroids this size or larger strike Earth roughly every 100 million years, based on the cratering record and observations of near-Earth objects. The dinosaurs dominated Earth for 160 million years, but they couldn't survive one bad day when a mountain fell from the sky. The extinction of the dinosaurs wasn't just a prehistoric curiosity, it was a preview of our own vulnerability. The same cosmic processes that ended the age of reptiles continue today, and objects capable of causing similar devastation regularly cross Earth's orbit. The only difference is that now we have the technology to see them coming, and perhaps, if we're lucky, to do something about it. At 7:17 a.m. on June 30th, 1908, something exploded over the remote Siberian wilderness, with the force of 1,000 Hiroshima bombs, flattening 2,150 square kilometers of forest, and creating one of the most enduring mysteries in the history of cosmic impacts. The Tunguska event, as it came to be known, began as a brilliant fireball streaking across the morning sky over central Siberia. Witnesses hundreds of kilometers away described seeing a column of blue light, nearly as bright as the sun, moving across the sky from southeast to northwest. The object was visible for several minutes before it exploded in the atmosphere above the remote Podkomonaya Tunguska River Valley. The explosion was heard over 1,000 kilometers away, in the town of Vanavara, 65 kilometers from the blast site. The shockwave was powerful enough to knock people off their feet and break windows. Seismic stations across Eurasia registered what appeared to be an earthquake, though the signals had characteristics unlike any tectonic event on record. But the most extraordinary effect was yet to come. The explosion launched so much debris into the upper atmosphere that it created brilliant noctilucent clouds, ice crystal formations in the mesosphere that reflected sunlight long after sunset. For several nights after the event, people across Europe reported that the night sky was so bright they could read newspapers outdoors at midnight. The atmospheric disturbance was detected as far away as Washington, D.C., where the Smithsonian Astrophysical Observatory recorded unusual optical phenomena. What makes the Tunguska event so mysterious is what investigators didn't find when they finally reached the remote blast site. The first scientific expedition didn't arrive until 1927, nearly 2 decades after the explosion, led by Soviet scientist Leonid Kulik. Kulik expected to find a massive crater and fragments of a meteorite that could be studied and potentially exploited for their iron content. Takawas with Agenta was Diri's what investigators didn't find when they finally reached the remote blast site. The first scientific expedition didn't arrive until 1927. Kulik expected to find a massive crater and fragments of a meteorite that could be studied and potentially exploited for their iron content. Instead, he found something far more puzzling: a radial pattern of destruction with no crater at the center. Trees were flattened in all directions from a central point, but at ground zero itself, the trees remained standing, stripped of their branches and bark, but still upright, like ghostly telephone poles pointing toward the sky. It was as if the explosion had occurred not on the ground, but several kilometers above it. The pattern of destruction told a clear story to anyone who understood the physics of explosions. The object, whatever it was, had exploded in the atmosphere at an altitude of approximately 5 to 10 kilometers above the Earth's surface. This aerial burst explained why there was no crater. The energy was released in the air, not on the ground, creating a downward-directed shock wave that flattened the forest in a radial pattern. Computer modeling suggests that the Tunguska object was probably a small asteroid or comet fragment, perhaps 40 to 60 meters in diameter, composed of relatively fragile material. As it plunged through Earth's atmosphere at cosmic velocity, the immense aerodynamic pressures caused it to fragment and explode before reaching the surface. Entawaz, Ivutusivan to Fisivan. The explosion released energy equivalent to 10 to 15 megatons of TNT, nearly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The lack of surviving fragments has fueled decades of speculation and investigation. Some researchers have proposed that the object was a small comet, composed primarily of ice and loosely bound rocky material that would have been completely vaporized by the explosion. Others suggest it was a rare type of stony asteroid with unusual structural properties that caused it to disintegrate completely in the atmosphere. What makes Tunguska particularly relevant to modern asteroid defense efforts is that it demonstrates how even relatively small cosmic objects can cause devastating regional destruction. An explosion like Tunguska, occurring over a populated area, could kill millions of people and cause economic damage comparable to a major war. Yet objects this size are extremely difficult to detect and track with current technology. The Tunguska event also highlighted our vulnerability to surprises from space. The object approached from the direction of the sun, making it effectively invisible to ground-based observers until the final moments before impact. Even today, with our sophisticated asteroid detection programs, objects approaching from the solar direction remain largely undetectable until they're dangerously close to Earth. Recent research has revealed that Tunguska-scale events may be more common than previously thought. Statistical analysis of fireball observations and atmospheric explosion detections suggests that objects capable of causing Tunguska-level destruction strike Earth approximately once every 300 to 500 years. This means that somewhere on Earth, a Tunguska-scale explosion is likely to occur within the next few centuries. The randomness of cosmic impacts means that the next Tunguska event could occur anywhere on Earth. If it happened over New York, London, Tokyo, or any other major metropolitan area, the death toll could exceed that of any natural disaster in human history. The explosion would flatten buildings over an area of thousands of square kilometers, trigger massive fires, and disrupt communications and transportation systems across entire regions. Perhaps most unsettling is the realization that we had no warning of the Tunguska event in 1908. And if a similar object approached Earth today, we might have only hours or days of advance notice, far too little time to mount any kind of defensive response. The Siberian wilderness absorbed the full force of a cosmic explosion that serves as a reminder that space regularly fires warning shots at our planet. The question isn't whether another Tunguska event will occur, but when and where, and whether next time we'll be as fortunate in its target selection. Right now, as you watch this video, there are over 28,000 known asteroids whose orbits bring them uncomfortably close to Earth, and astronomers discover about 30 new ones every single week. Each discovery represents a cosmic bullet that was previously unknown, flying through space on a trajectory that could potentially intersect with our planet's orbit. NASA's current definition of a potentially hazardous asteroid is any object larger than 140 meters, SIME, that comes within 7.5 million kilometers of Earth's orbit. That might sound like a safe distance, but in cosmic terms, it's like threading a needle while blindfolded. These objects are traveling at speeds of 20 to 50 kilometers per second. And small changes in their orbits, caused by gravitational interactions with planets or the subtle pressure of sunlight, can shift their trajectories in ways that bring them dangerously close to our planet. The asteroid monitoring systems we've built represent humanity's first line of defense against cosmic impacts, but they also reveal just how active and dangerous our cosmic neighborhood really is. The Catalina Sky Survey, Linear, NEOWISE, and other detection programs scan the skies every night, photographing the same regions repeatedly to identify moving objects against the background of stars. It's like conducting a cosmic census of everything that might one day kill us. But the statistics are sobering. Despite decades of observation, we've probably identified only about 90% of the kilometer-sized asteroids that pose extinction-level threats to Earth. For smaller objects, the Tunguska-class asteroids that could destroy cities, we've found less than 30% of the estimated population. This means that thousands of city-killer asteroids remain undiscovered, invisible, until they're detected just days or weeks before potential impact. The near-miss encounters we've documented read like a catalogue of cosmic close calls. In 2013, asteroid 2012, DA14, passed just 27,700 kilometers from Earth, closer than our geostationary satellites. On the same day, the Chelyabinsk meteor, a completely unrelated object, exploded over Russia with the force of 30 atomic bombs. The coincidence was terrifying. 2 separate asteroid encounters on the same day, demonstrating that our planet exists in a genuine cosmic shooting gallery. Asteroid 2019, dubbed the City Killer, approached within 70,000 kilometers of Earth in July 2019, about 1/5 the distance to the Moon. This 100-meter wide object was discovered just 24 hours before its closest approach, traveling so fast that even if we had detected it earlier, there would have been no time to mount any kind of defensive response. It was a stark reminder that our detection systems still have critical blind spots. Perhaps most unnerving was the discovery of asteroid 2020 QG, which holds the record for the closest known non-impacting asteroid flyby. This 3 to 6 meter object passed just 2,950 kilometers above the Earth's surface, closer than some satellites. It wasn't detected until 6 hours after it had already passed, highlighting how objects can slip through our detection network and surprise us completely. The detection systems themselves face significant limitations. Ground-based telescopes can't observe during daylight hours and are limited by weather and atmospheric conditions. Objects approaching from the direction of the sun remain largely invisible until they're very close to Earth. The Chelyabinsk meteor, which injured over 1,500 people, approached from exactly this blind spot. Space-based detection systems like NEOWISE have revolutionized our ability to find asteroids, but they operate with limited lifespans and narrow fields of view. The European Space Agency's planned Hera mission and NASA's proposed NEO Surveyor represent the next generation of asteroid detection technology, but they won't be operational for several more years. Even when we do detect potentially dangerous asteroids, the lead time for defensive action can be frustratingly short. Asteroid 2022, AP7, discovered in 2022, is a 1.5-kilometer-wide object that crosses Earth's orbit and could potentially impact our planet in the future. But its orbital period is so long that we won't know if it poses an imminent threat for decades or centuries. The gravitational keyhole effect adds another layer of uncertainty to impact predictions. These are small regions of space where a gravitational encounter with Earth could alter an asteroid's orbit just enough to guarantee a future collision. Asteroid 99942 Apophis, once considered a serious impact threat for 2029, will pass through just such a keyhole, and whether it hits Earth in 2036 depends on its exact trajectory through a region of space just a few hundred meters wide. Our expanding catalogue of near-Earth asteroids reveals a universe far more crowded and dangerous than we once imagined. Every new discovery reminds us that we're not alone in our orbital space. We share it with thousands of cosmic projectiles, any one of which could end our technological civilization, or even our species. The race between discovery and disaster continues every night as telescopes scan the skies, and we can only hope that when the next major threat is identified, we'll have enough warning to do something about it. When cosmic catastrophes strike, they don't always announce themselves with spectacular explosions or visible devastation. Often, the most deadly effects are completely invisible, high-energy radiation that silently dismantles life at the most fundamental level, cell by cell, molecule by molecule, until entire ecosystems collapse from within. To understand how cosmic threats can sterilize planets, we need to journey into the microscopic world where life's most basic processes unfold. Every living cell on Earth depends on the precise structure of complex molecules, particularly DNA, proteins, and the lipid membranes that hold cellular components together. These biological molecules have evolved over billions of years to function within Earth's relatively benign radiation environment, protected by our atmosphere and magnetic field from the harsh realities of space. But when gamma-ray bursts, solar storms, or cosmic ray bombardments overwhelm our planetary defenses, they flood the biosphere with radiation energetic enough to shatter the chemical bonds that hold life together. Gamma rays, carrying energies millions of times higher than visible light, tear through living tissue like cosmic bullets, leaving trails of molecular destruction in their wake. The most immediate target is DNA, the blueprint molecule that contains the instructions for all life on Earth. When high-energy radiation strikes a DNA molecule, it can break the double helix structure, delete genetic information, or cause harmful mutations that turn healthy cells into cancer cells. A single gamma-ray photon carries enough energy to break hundreds of chemical bonds, potentially damaging multiple genes simultaneously. But DNA damage is just the beginning of radiation's assault on life. High-energy particles also generate cascades of secondary reactions, creating highly reactive molecules called free radicals that continue the destruction long after the initial radiation exposure. Decay de-aging through de-aging, second of free DA. These free radicals attack cell membranes, proteins, and other critical cellular components, spreading damage throughout the cell like a molecular wildfire. The cellular repair mechanisms that normally fix routine DNA damage become overwhelmed when radiation doses exceed the capacity of these biological maintenance systems. Cells faced with irreparable damage typically trigger programmed cell death, causing tissues and organs to fail as too many cells die simultaneously. This is why acute radiation syndrome, also known as radiation poisoning, begins with the failure of rapidly dividing cells in the bone marrow, digestive system, and immune system. What makes cosmic radiation particularly devastating is its penetrating power. Unlike the relatively low-energy radiation from medical X-rays or nuclear fallout, the gamma rays from a nearby gamma-ray burst, or the high-energy particles from extreme solar storms, can penetrate deep into organisms, even those sheltered underground or underwater. The most energetic cosmic rays can pass through several meters of rock, making it nearly impossible for life to find adequate shielding. The scale of biological destruction depends critically on the dose rate, how quickly the radiation exposure occurs. The same total amount of radiation delivered over years might cause increased cancer rates and gradual ecosystem changes. But if delivered over hours or days, it can cause immediate mass die-offs across multiple species. Cosmic catastrophes typically deliver their radiation loads very rapidly, maximizing the biological damage. Different types of life show dramatically different sensitivity to radiation. Bacteria and other microorganisms tend to be much more radiation resistant than complex multicellular organisms. This is partly because their simpler cellular structure provides fewer targets for radiation damage, partly because many bacteria have evolved extraordinarily efficient DNA repair mechanisms. Some extremophile bacteria can survive radiation doses thousands of times higher than what would be lethal to humans. This differential sensitivity means that cosmic radiation events don't just kill, they fundamentally reshape ecosystems by selectively eliminating the most complex forms of life while leaving simpler organisms intact. A gamma-ray burst that sterilizes all complex life on a planet might leave behind a world dominated by radiation-resistant bacteria, effectively resetting evolution to its earliest stages. The atmospheric effects of cosmic radiation add another layer of biological destruction. High-energy particles striking Earth's atmosphere generate cascades of secondary particles and create nitrogen oxides that destroy the ozone layer. With the ozone shield compromised, the sun's ultraviolet radiation reaches the surface at levels that can kill exposed organisms and prevent photosynthesis in plants and phytoplankton. This creates a deadly combination: direct radiation damage from the cosmic event itself, followed by prolonged exposure to increased ultraviolet radiation as the ozone layer recovers. The result is a 1-2 punch that can devastate both terrestrial and marine ecosystems simultaneously. Marine life faces particular challenges during cosmic radiation events. While water provides some shielding against radiation, the organisms that form the base of oceanic food webs, phytoplankton, live near the surface where they're most vulnerable to both direct cosmic radiation and increased UV exposure. The collapse of these microscopic primary producers can trigger ecosystem-wide collapse that propagates up through the entire marine food chain. Recent research has revealed that cosmic radiation may have played a larger role in Earth's history than previously recognized. Some mass extinction events in the fossil record show patterns consistent with radiation-induced ecosystem collapse, including the preferential extinction of large, complex organisms and the survival of smaller, simpler species. The most chilling aspect of radiation's invisible death is its inevitability. Unlike asteroid impacts that might miss, or volcanic eruptions we might survive in shelters, radiation from cosmic sources travels at the speed of light and penetrates all but the most extreme shielding. When a gamma-ray burst's radiation reaches Earth, every living thing on the planet's surface is simultaneously exposed to potentially lethal doses, with no possibility of escape or advance warning. This invisible apocalypse doesn't announce itself with earthquakes or fire from the sky. It simply makes living impossible, one broken molecule at a time. Earth's atmosphere isn't just the air we breathe. It's a finely tuned, multi-layered shield that has protected life for billions of years. But when cosmic forces strike this protective barrier, they don't just damage it. They trigger cascading chemical reactions that can systematically dismantle the very mechanisms that make our planet habitable. The destruction begins in the stratosphere, where high-energy particles from gamma-ray bursts or extreme solar storms collide with nitrogen and oxygen molecules 20 to 50 kilometers above our heads. These collisions create nitrogen oxides, normally harmless compounds that exist in trace amounts, but during cosmic events, they're produced in quantities that transform them into atmospheric poison. Nitrogen oxides become catalytic destroyers of ozone, each molecule capable of breaking apart hundreds of ozone molecules in a chain reaction that continues for months. The ozone layer, which absorbs 99% of the sun's lethal ultraviolet radiation, can be depleted by 75% or more during major cosmic events. What took millions of years of atmospheric evolution to create can be destroyed in weeks. But ozone destruction is just the beginning of atmospheric collapse. The same chemical processes that eliminate our UV shield also produce other reactive compounds that alter the fundamental chemistry of the atmosphere. Nitric acid forms in the stratosphere and rains down to acidify soils and water bodies. Hydroxyl radicals, nature's atmospheric detergent, are depleted, allowing greenhouse gases and pollutants to accumulate to dangerous levels. The temperature structure of the atmosphere becomes chaotic during cosmic events. The stratosphere, normally heated by ozone absorption of UV radiation, begins cooling as ozone disappears. Meanwhile, the absorption of high-energy particles adds energy at different altitudes, creating temperature inversions and disrupting normal atmospheric circulation patterns. Weather systems become unpredictable, and the jet streams that guide storm systems can shift dramatically. These atmospheric changes create feedback loops that amplify the destruction. As the ozone layer thins and UV radiation increases, phytoplankton in the oceans begin dying en masse. These microscopic organisms normally absorb billions of tons of carbon dioxide from the atmosphere, but their death reverses this process, releasing stored carbon and accelerating climate change. The ocean's role as a carbon sink collapses just when Earth needs it most. On land, the increased UV radiation penetrates deeper into forest canopies, damaging plant DNA and disrupting photosynthesis. Plants respond by producing more UV screening compounds, but this defensive response reduces their growth rate and nutritional value. Yuncha, crops fail, forests become stressed, and the terrestrial carbon cycle begins breaking down. The magnetic field interactions during extreme space weather events add another layer of atmospheric disruption. When coronal mass ejections compress Earth's magnetosphere, they can dump massive amounts of energetic particles directly into the polar regions. These particles heat the upper atmosphere, causing it to expand and change density. Satellites experience increased drag and can be pulled out of their orbits, while radio communications become impossible due to ionospheric disturbances. Perhaps most insidiously, the atmospheric damage persists long after the original cosmic event has passed. Ozone destruction continues for months as the nitrogen oxide catalysts remain active in the stratosphere. The changed atmospheric chemistry takes years to return to normal, creating an extended period of vulnerability during which Earth's protective systems remain compromised. Computer models reveal that the atmospheric effects of cosmic events can be more devastating than the direct radiation exposure. While gamma rays from a distant stellar explosion might last only minutes, the atmospheric damage they cause can persist for years, creating a prolonged period during which Earth's surface remains exposed to lethal radiation levels. The geological record preserves evidence of these atmospheric catastrophes. Ice cores from Greenland and Antarctica contain chemical signatures of past cosmic events, spikes in nitrates and other compounds produced when space radiation strikes the atmosphere. These same ice cores show correlations between cosmic events and periods of climate change, suggesting that atmospheric disruption from space may have influenced Earth's climate history more than we previously realized. Modern atmospheric monitoring systems can detect the early signs of cosmic atmospheric damage, but they also reveal how quickly our protective systems can be compromised. During major solar storms, ozone depletion can be measured in real time, and atmospheric chemistry changes are observable within hours of the initial space weather event. The fragility of our atmospheric shield becomes apparent when we compare Earth to other planets. Mars once had a substantial atmosphere but without a strong magnetic field to protect it from solar wind erosion. That atmosphere was gradually stripped away over millions of years. Venus has a thick atmosphere, but runaway greenhouse effects have made its surface uninhabitable. Earth's atmosphere exists in a delicate balance that cosmic events can disrupt in ways that cascade through the entire climate system, reminding us that our planet's habitability depends on protective systems that are far more fragile than they appear. The most terrifying aspect of cosmic threats isn't their direct impact. It's how a single event in space can trigger an unstoppable cascade of disasters that amplify each other until they reshape the entire planet. Like dominoes arranged in an intricate pattern, Earth's interconnected systems can transform a brief cosmic disturbance into a prolonged global catastrophe that persists for years or decades. Understanding this domino effect requires us to recognize that Earth isn't a collection of separate systems, but rather an integrated network where the atmosphere, oceans, climate, and biosphere are all intimately connected. So Omarius serve or intimately connected. When a cosmic event disrupts one component of this network, the effects ripple through every other system, often in ways that are more destructive than the original disturbance. Consider what happens when a gamma-ray burst strikes Earth's atmosphere. The initial gamma radiation exposure lasts only seconds or minutes, but those brief moments of high-energy bombardment set in motion a sequence of events that can persist for years. The gamma rays create nitrogen oxides that begin destroying the ozone layer. But this is just the first domino to fall. As the ozone layer thins over the following weeks, ultraviolet radiation levels at Earth's surface increase dramatically. Marine phytoplankton, the microscopic organisms that form the foundation of oceanic food webs, begin dying from UV radiation exposure. These tiny creatures might seem insignificant, but they produce roughly half of Earth's oxygen and absorb enormous quantities of carbon dioxide from the atmosphere. The death of phytoplankton triggers the second wave of dominoes. Oxygen production slows while carbon dioxide absorption stops, beginning to alter the atmospheric composition. Fish, whales, and other marine life that depend on phytoplankton for food begin to starve, causing population crashes that ripple up through the entire marine food web. Dead marine organisms sink to the ocean floor, where their decomposition consumes oxygen and releases greenhouse gases. On land, the increased UV radiation begins damaging plant DNA and disrupting photosynthesis. Forests, already stressed by the changed atmospheric chemistry, become more susceptible to disease, insect infestations, and wildfire. Fire, as vegetation dies, it releases stored carbon dioxide, accelerating the greenhouse effect and contributing to rapid climate change. The atmospheric chemistry changes trigger additional dominoes, while with less vegetation to absorb carbon dioxide and more dead organic matter releasing greenhouse gases, global temperatures begin rising. This warming accelerates the melting of polar ice caps and permafrost, releasing even more greenhouse gases that have been locked away for thousands of years. As ice caps melt, sea levels rise and ocean currents begin changing. The thermohaline circulation, the global conveyor belt of ocean currents that regulates planetary climate, can be disrupted by changes in water temperature and salinity. When this circulation slows or stops, regional climates can shift dramatically, turning fertile areas into deserts and altering precipitation patterns worldwide. The hydrological cycle becomes increasingly chaotic as atmospheric temperatures rise and circulation patterns change. Some regions experience severe droughts, while others face unprecedented flooding. Agricultural systems, already stressed by increased UV radiation and changed atmospheric chemistry, begin failing as growing conditions become unpredictable. These environmental changes trigger social and economic dominoes that can be as devastating as the physical effects. As crops fail and fresh water becomes scarce, food prices skyrocket and mass migration begins. Political instability follows as governments struggle to manage resource shortages and population displacement. International conflicts may erupt over remaining fertile land and freshwater resources. The collapse of technological infrastructure adds another layer to the cascade. If the cosmic event included electromagnetic effects, such as those from a major solar storm, power grids, communication networks, and satellite systems may have failed during the initial event. The inability to coordinate disaster response or maintain food distribution networks accelerates social collapse. Medical systems become overwhelmed as radiation exposure increases cancer rates, and immune system damage makes populations more susceptible to infectious diseases. The combination of malnutrition, environmental stress, and reduced medical capacity can trigger disease outbreaks that further destabilize society. Perhaps most insidiously, the domino effect can make recovery increasingly difficult as time passes. Each failed system makes it harder for the remaining systems to function properly. Without reliable agriculture, it becomes impossible to support the large populations needed for industrial society. Without industrial capacity, it becomes impossible to manufacture the technology needed to monitor and respond to ongoing environmental changes. The paleontological record suggests that this domino effect has occurred multiple times in Earth's history. The Permian-Triassic extinction event, which eliminated 96% of marine species 252 million years ago, may have been triggered by a cosmic event that initiated cascading environmental changes. The extinction took place over thousands of years, suggesting that the initial trigger set in motion long-term processes that continued long after the original disturbance had passed. Modern Earth may be particularly vulnerable to domino effect catastrophes because our interconnected global systems can transmit disruptions faster and farther than ever before. A cosmic event that destroys satellite communications can instantly disrupt financial markets worldwide. Climate changes that affect agricultural regions can trigger food shortages on other continents within months. Computer models of cosmic impact scenarios reveal that the domino effects often cause more long-term damage than the original event. A gamma-ray burst that lasts 10 seconds might trigger climate changes that persist for decades. An asteroid impact that takes minutes might initiate ecosystem collapses that continue for millions of years. The most sobering aspect of the domino effect is its irreversibility. Once certain thresholds are crossed, when key species go extinct, when atmospheric chemistry changes beyond certain limits, when climate systems shift into new stable states, the cascade becomes self-perpetuating and increasingly difficult to reverse. This is why cosmic threats represent existential risks to human civilization and complex life in general. It's not just the direct effects we need to fear, but the possibility that a brief cosmic disturbance could push Earth's interconnected systems past critical tipping points, triggering changes that continue long after the original threat has passed. The domino effect transforms cosmic events from temporary disturbances into permanent alterations of Earth's habitability, reminding us that in our interconnected world, no disaster exists in isolation, and the most dangerous threats are often those that set in motion changes we cannot stop. 25,000 miles above your head, an invisible war is raging. Earth's magnetic field, our planet's ancient shield against cosmic destruction, battles constantly against the solar wind, cosmic rays, and the violent electromagnetic storms that sweep through our solar system. Most of the time, our magnetic defenses win these battles, deflecting deadly radiation and protecting the fragile biosphere below. But sometimes, space weather overwhelms even these formidable defenses. And when that happens, the consequences reach all the way down to the surface of our planet. Earth's magnetosphere is one of the most remarkable structures in our solar system, a vast, invisible bubble that extends far into space, shaped by the constant pressure of the solar wind into a teardrop configuration that stretches millions of kilometers behind our planet. This is one of the most remarkable structures in our solar system, a vast invisible bubble. This magnetic cocoon is generated deep within Earth's core, where liquid ion convection currents create electrical currents that produce our planetary magnetic field. But this protective barrier isn't impenetrable. It's more like a flexible membrane that can be compressed, stretched, and in extreme cases, temporarily breached by the forces that space weather throws against it. When a coronal mass ejection, a billion-ton cloud of magnetized plasma, slams into Earth's magnetosphere, the collision can compress our magnetic field to half its normal size, allowing dangerous radiation to penetrate much deeper into our planetary environment than usual. The physics of these magnetic collisions are both elegant and terrifying. When the twisted magnetic fields, carried by a CME, interact with Earth's magnetic field lines, they can undergo a process called magnetic reconnection, a phenomenon where magnetic field lines break apart and reconnect in new configurations, releasing enormous amounts of energy in the process. This energy doesn't just dissipate harmlessly into space. It accelerates charged particles to tremendous speeds and injects them directly into Earth's radiation belts. These radiation belts, discovered by the first US satellite Explorer 1 in 1958, normally serve as a secondary defense system, trapping energetic particles in magnetic bottles high above the atmosphere. But during extreme space weather events, these belts can become overloaded with particles, creating radiation environments so intense that they can permanently damage or destroy satellites passing through them. The magnetosphere's protective power becomes most apparent at the poles, where the magnetic field lines converge and channel energetic particles down into the upper atmosphere. This is what creates the aurora, those beautiful dancing lights that mark the points where space weather directly penetrates our planetary defenses. But auroras are more than just pretty light shows. They're visible evidence of our magnetic shield under attack. During major geomagnetic storms, the aurora can appear hundreds of miles farther from the poles than normal, indicating that our magnetic defenses have been severely compromised. Hove intues deviation. The Carrington event of 1859 produced auroras as far south as the Caribbean, meaning that space weather had overwhelmed Earth's magnetic field so completely that deadly radiation was penetrating to latitudes where millions of people now live. What makes modern space weather particularly dangerous is that our technology has evolved to occupy the very regions where these magnetic battles take place. Our communications satellites orbit in the magnetosphere. Our astronauts work beyond the protection of Earth's atmosphere, and our power grids span thousands of miles of Earth's surface, making them perfect antennas for capturing the electrical currents that geomagnetic disturbances induce. The magnetic field itself is not constant. It varies in strength and can even reverse completely over geological timescales. Right now, Earth's magnetic field is weakening at a rate of about 5% per century, and the magnetic North Pole is moving towards Siberia at an accelerating pace. Some scientists believe we may be entering the early stages of a magnetic field reversal, a process that could take thousands of years to complete and leave Earth with greatly reduced magnetic protection during the transition. Paleomagnetic studies reveal that these reversals have occurred hundreds of times in Earth's history, with the magnetic field weakening dramatically or even disappearing entirely for periods of hundreds or thousands of years. During these vulnerable periods, cosmic radiation exposure at Earth's surface would increase significantly, potentially affecting human health, electronics, and the upper atmosphere's chemistry. Computer simulations of extreme space weather events reveal scenarios where Earth's magnetosphere could be so severely compressed that the International Space Station would find itself outside our magnetic protection, exposing astronauts to potentially lethal radiation doses. Lethal radiation doses, ground-based power systems could experience induced currents strong enough to melt major transformers, while GPS and communication satellites could be permanently disabled by radiation damage. The magnetic field's protective power extends beyond just deflecting charged particles. It also helps preserve Earth's atmosphere by preventing the solar wind from gradually stripping it away over geological timescales. Mars, which lacks a strong global magnetic field, has had much of its atmosphere eroded by this process, transforming it from a potentially habitable world into the cold, dry planet we see today. Recent observations have revealed that Earth's magnetosphere can develop temporary cracks during certain types of space weather events, allowing solar wind particles to penetrate directly to the upper atmosphere. These breaches heal quickly, but they demonstrate that our magnetic shield isn't the impregnable barrier we once thought it was. As space weather monitoring improves, we're discovering that our magnetic defenses face a more constant barrage than previously realized. The solar wind never stops. Cosmic rays continuously probe for weaknesses, and major storms strike with enough force to reshape the entire magnetosphere. Our planet's magnetic field has protected Earth for billions of years, but it's fighting a war that it cannot ultimately win. And when it finally fails, we'll discover just how hostile the universe really is. In the span of a few hours, a single coronal mass ejection could transform our hyperconnected world into something resembling the 19th century, except with 8 billion people dependent on technologies that no longer work. Kius, a few inti. Wantaisamavi sevashti sevachiv indin sevashti. Twesmi my fufa indeed and sevashti. Teatasam dis. Steerden seerden teatasam dis. Ketbeatasam dis. Wantasamishti sevashti sevashti sevashti. Wantasam dis. The collapse wouldn't be gradual or manageable. It would be sudden, simultaneous, and catastrophic. The first casualties would be our satellites, those technological marvels that have become so integral to modern life that we barely notice their existence until they fail. More than 4,000 active satellites orbit Earth, forming an invisible infrastructure that enables everything from weather forecasting to international banking. These delicate electronic systems, designed to operate in the harsh environment of space, represent millions of hours of engineering and billions of dollars in investment. And they're all vulnerable to the electromagnetic fury that major space weather events can unleash. When energetic particles from a coronal mass ejection strike satellite electronics, they cause what engineers call single-event upsets, cosmic rays that flip individual bits in computer memory, causing software to crash or hardware to malfunction. During severe space weather events, these upsets can cascade through entire satellite systems, causing permanent damage to critical components that cannot be repaired or replaced remotely. The GPS constellation, consisting of at least 24 satellites providing precise timing and location data, would likely suffer widespread failures during a major space weather event. But GPS isn't just for navigation. It provides the ultra-precise timing signals that synchronize everything from cellular phone networks to financial trading systems to power grid operations. When GPS timing fails, the effects ripple through virtually every aspect of modern infrastructure. Power grids represent perhaps the most vulnerable and critical component of our technological civilization. These vast networks of transmission lines, transformers, and control systems weren't designed to handle the massive geomagnetically induced currents that major space weather events can generate. During the 1989 Quebec blackout, a relatively modest geomagnetic storm induced currents that tripped protective systems and collapsed the entire provincial power grid in less than 90 seconds. But a Carrington-level event would be far more devastating. The high-voltage transmission lines that carry electricity across continents would act like enormous antennas, capturing and concentrating the electromagnetic energy from the space weather event. With a Carrington-level event would be far more devastating. The induced currents, potentially hundreds of times stronger than normal operating currents, would flow through transformers that simply cannot handle such massive electrical loads. These high-voltage transformers are the critical vulnerability in our electrical infrastructure. Weighing hundreds of tons and custom-built for specific applications, they can take months or years to manufacture and replace. A major space weather event could damage or destroy hundreds of these transformers simultaneously across multiple continents, creating a recovery challenge unlike anything in human history. The cascading effects of power grid failure would be immediate and devastating. Modern water treatment plants depend on electricity to operate purification systems and pumps. Without power, most cities would run out of clean drinking water within 72 hours. Sewage treatment systems would fail, creating public health emergencies. Food distribution networks, dependent on refrigeration and electronic inventory systems, would collapse within days. Financial systems, entirely dependent on electronic communications and computer networks, would cease functioning. ATMs would stop working. Credit card systems would fail, and electronic banking would become impossible. The global economy, built on just-in-time delivery and electronic transactions, would grind to a halt. Communications infrastructure would suffer multiple simultaneous failures. Cell phone networks depend on precise timing from GPS satellites and require continuous electrical power to operate base stations. Internet traffic, routed through systems that depend on GPS timing and satellite links, would face massive disruptions. Even landline telephone systems, seemingly more robust, would fail as their electronic switching systems lost power and their backup batteries drained. The medical consequences would be catastrophic. Hospitals would be forced to operate on emergency generators with limited fuel supplies. Patients dependent on electrically powered medical devices, dialysis machines, ventilators, insulin pumps, would face life-threatening situations. The inability to maintain cold storage for medications and vaccines would create additional medical emergencies. Transportation systems would face unprecedented chaos. Modern vehicles depend on electronic systems that could be damaged by electromagnetic pulses from space weather events. Air traffic control systems would fail, grounding thousands of aircraft and stranding millions of passengers. Railway systems, dependent on electronic signaling and control systems, would shut down. Even ships at sea would lose GPS navigation and satellite communications. The psychological and social effects might be even more devastating than the technological failures. A population accustomed to instant global communication and 24/7 access to information would suddenly find itself isolated and uninformed. Without television, radio, or internet, rumors and panic could spread faster than accurate information about the scope and duration of the crisis. Emergency response systems, designed for localized disasters, would be overwhelmed by the scale of simultaneous failures across multiple regions. First responders would lose radio communications, have no access to computerized dispatch systems, and face fuel shortages as gas stations lost the ability to pump fuel. The coordinated disaster response that modern emergency management depends on would become impossible. Recovery from such an event would face unprecedented challenges. The manufacturing facilities needed to produce replacement transformers and electronic components would themselves be affected by the power grid failures. International cooperation, normally coordinated through satellite communications and electronic banking systems, would be severely hampered. The economic resources needed for recovery would be tied up in non-functioning financial systems. Computer models suggest that recovery from a major space weather disaster could take anywhere from months to decades, depending on the severity of the damage and the effectiveness of emergency response. A 2008 National Academy of Sciences study estimated that a Carrington-level event could cause $1.2 trillion in damage in the United States alone, with recovery times of 4–10 years. Perhaps most sobering is the realization that we've never actually tested our modern technological infrastructure against a truly severe space weather event. The most powerful geomagnetic storms of the satellite and internet era have been relatively modest compared to historical events like the Carrington storm. We're conducting a vast, uncontrolled experiment with the technological foundations of human civilization, and we won't know the results until the next major space weather event strikes. The technology that has lifted billions out of poverty, connected the world, and enabled unprecedented human achievement could become humanity's greatest vulnerability. When the sun decides to remind us who really controls our corner of the universe. Modern civilization hangs by a thread so thin that most people never realize it exists until it snaps. That thread is the intricate web of interdependent systems that keep 8 billion people fed, housed, healthy, and safe. When cosmic forces sever that thread, the collapse isn't just about losing electricity or internet access. It's about the systematic unraveling of everything that makes our complex society possible. The fragility becomes apparent when we trace the dependency chains that connect our most basic needs to the technological systems that space weather can destroy. Food production in developed nations depends entirely on mechanized agriculture, powered by electricity and guided by GPS systems. Modern farms use satellite-controlled tractors, GPS-guided irrigation systems, and computerized monitoring of soil conditions and crop health. Without these technologies, agricultural productivity could drop by 50% or more, creating immediate food shortages in regions that haven't maintained traditional farming knowledge. But the food supply chain extends far beyond the farm. Processing facilities, refrigerated, transportation, and distribution centers all depend on reliable electricity and sophisticated logistics networks. Just-in-time inventory systems, designed for efficiency rather than resilience, mean that most grocery stores carry only 3–7 days worth of food. When the supply chain breaks, urban areas, where most of the world's population now lives, quickly face starvation. Water systems represent another critical vulnerability. Modern cities depend on electric pumps to move water from treatment plants to consumers, often against gravity through complex distribution networks. Without power, water pressure drops, and contamination can enter the system through backflow, Most urban residents have no alternative water sources and limited water storage, making them completely dependent on centralized systems that space weather can cripple. The medical infrastructure that keeps populations healthy would face cascading failures during a prolonged space weather disaster. Hospitals depend on sophisticated electronic equipment, refrigerated medications, and reliable power for everything from life support systems to basic lighting. Patients requiring dialysis, insulin, or other regular treatments would face life-threatening situations within days. The inability to manufacture or distribute medications would create additional medical emergencies that could persist for months or years. Social order itself becomes precarious when the systems that maintain it fail simultaneously. Police and emergency services depend on radio communications, computer databases, and transportation systems that could all be compromised during major space weather events. Without the ability to coordinate responses or maintain communications, law enforcement becomes impossible over large areas. Economic systems, built on electronic transactions and global communications, would suffer immediate and potentially permanent collapse. The 2008 financial crisis, triggered by the failure of a few major banks, demonstrates how quickly economic confidence can evaporate. A space weather event that simultaneously disrupts banking systems, disables communication networks, and destroys electronic records could trigger an economic collapse that makes historical depressions seem mild by comparison. The psychological impact of sudden technological isolation could be as devastating as the physical hardships. Populations, accustomed to instant global communication, would suddenly find themselves cut off from information about family members, friends, and the broader situation. Rumors and panic could spread faster than accurate information, potentially triggering social unrest that authorities would be unable to control with compromised communications and transportation systems. Government continuity plans, designed for natural disasters or terrorist attacks, assume that most infrastructure will remain functional during crisis response. But space weather disasters could simultaneously disable the communications, transportation, and power systems that government coordination depends on. Federal, state, and local authorities might be unable to communicate with each other or coordinate disaster response efforts. International cooperation, essential for managing global crises, would face unprecedented challenges. Diplomatic communications depend on satellite links and internet connectivity. International financial systems that enable countries to purchase emergency supplies or provide aid would be non-functional. The global supply chains that allow countries to specialize in particular industries would be severed, forcing nations to become self-sufficient in areas where they may lack necessary resources or expertise. Perhaps most concerning is how quickly modern populations could lose essential knowledge and skills. Most people in developed nations don't know how to grow food, preserve meat without refrigeration, navigate without GPS, or perform basic medical procedures without modern equipment. The transition from a high-tech to a low-tech society would be devastating for populations that have no experience with pre-industrial survival methods. Recovery would face the challenge of rebuilding complex systems with a workforce that lacks the knowledge and tools to maintain them. The manufacturing facilities needed to produce transformers, electronics, and other critical components might themselves be damaged. The global supply chains needed to obtain raw materials and specialized components would be disrupted. The thread that holds our civilization together is strong enough to support incredible complexity and prosperity, but it's also thin enough that cosmic forces beyond our control can sever it in hours, leaving billions of people to rediscover what survival means in a world where the technology they depend on has suddenly stopped working. In a nondescript building in Maryland, computers process data from dozens of telescopes around the world, scanning the skies for objects that could end human civilization. Every night, automated systems photograph millions of stars, looking for the telltale movement that indicates an asteroid or comet crossing Earth's orbital path. It's a cosmic game of needle in a haystack, where finding the wrong needle could mean the difference between survival and extinction. The modern asteroid detection network represents one of humanity's most important technological achievements, even though most people have never heard of programs like Linear, Neowise, or the Catalina Sky Survey. These systems operate around the clock, taking millions of images of the night sky and processing them through sophisticated software designed to identify any object moving against the background of distant stars. The detection process itself is elegantly simple, but computationally intensive. Telescopes photograph the same regions of sky multiple times over the course of a night, typically taking 4 images of each field, separated by precise time intervals. Computer algorithms then compare these images, looking for points of light that have moved between frames. Asteroids and comets appear as moving dots, while stars and galaxies remain stationary. But finding these cosmic threats is only the beginning. Once a potentially dangerous object is detected, astronomers face the challenge of determining its precise orbit, a calculation that requires observations spanning weeks or months to achieve the accuracy needed for long-term predictions. This is where international cooperation becomes essential, as observatories around the world contribute additional observations to refine orbital calculations. NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory serves as the central clearinghouse for asteroid threat assessment. Scientists there use sophisticated computer models to calculate the probability of future impacts, taking into account not just the asteroid's current trajectory, but also the subtle forces that can alter its orbit over time. Gravitational perturbations from planets, pressure from solar radiation, and even the Yarkovsky effect, where absorbed and re-radiated sunlight can act like a tiny thruster. The space-based component of our early warning system adds crucial capabilities that ground-based telescopes cannot provide. NASA's Neowise mission, using an infrared space telescope, can detect asteroids approaching from the direction of the Sun, objects that remain invisible to ground-based observers until they're dangerously close to Earth. The infrared signatures also provide valuable information about asteroid composition and size, helping scientists assess the potential damage from future impacts. Solar storm monitoring requires an entirely different set of technologies. The Solar Dynamics Observatory, stationed in Earth orbit, watches the Sun continuously with instruments sensitive to multiple wavelengths of light, looking for the magnetic field changes that precede coronal mass ejections. Ground-based solar observatories around the world contribute additional observations, creating a global network that monitors our star's activity 24 hours a day. The Deep Space Climate Observatory, positioned at the L1 Lagrange point between Earth and the Sun, serves as our most advanced early warning system for space weather. From this vantage point, 1.5 million kilometers from Earth, it can detect coronal mass ejections about 15–60 minutes before they reach our planet, providing just enough warning time for satellite operators to put their systems into protective modes and power grid operators to prepare for geomagnetic disturbances. Gamma-ray burst detection relies on a constellation of satellites equipped with gamma-ray detectors. The Fermi Gamma-ray Space Telescope and Swift Gamma-ray Burst mission can detect these cosmic explosions within seconds and immediately alert ground-based observatories to begin follow-up observations. While we cannot predict when or where gamma-ray bursts will occur, rapid detection allows scientists to study their aftermath and better understand these cosmic weapons. The challenge of monitoring cosmic threats extends beyond just detection technology. The data processing requirements are enormous. The Large Synoptic Survey Telescope, scheduled to begin operations soon, will generate 20 terabytes of data every night. Will generate 20 terabytes of data every night. Advanced machine learning algorithms are being developed to automatically classify detected objects and identify the most potentially threatening ones for immediate human attention. Perhaps most critically, these early warning systems depend on international cooperation and data sharing. Asteroid threats don't respect national boundaries, so the detection networks share their data freely among nations. The Minor Planet Center, operated by the International Astronomical Union, serves as the global clearinghouse for asteroid and comet discoveries, ensuring that potentially dangerous objects are tracked by multiple observatories worldwide. Despite these sophisticated systems, significant gaps remain in our cosmic surveillance network. Objects approaching from the direction of the Sun can remain undetected until hours before impact. Very dark asteroids reflect so little sunlight that they're nearly invisible until they're very close to Earth, and our detection capabilities drop off rapidly for objects smaller than 100 meters, still large enough to cause regional devastation if they impact populated areas. The Watchers of the Sky work tirelessly to provide advance warning of cosmic threats, but they're racing against a universe that doesn't provide guarantees about when the next cosmic catastrophe will strike. In the pre-dawn darkness of the Arizona desert, astronomer Catalina Christensen adjusts the focus on a telescope that has discovered more potentially dangerous asteroids than any other instrument in history. As part of the Catalina Sky Survey, she's one of fewer than 100 people worldwide whose primary job is hunting for objects that could end human civilization. Tonight, like every clear night for the past 20 years, she'll scan the skies for cosmic threats that most of humanity will never know existed. These cosmic sentinels work in relative obscurity, their discoveries rarely making headlines unless an asteroid passes particularly close to Earth. Yet they represent humanity's first and most critical line of defense against cosmic catastrophe. Without their nightly vigil, we would be flying blind through a cosmic shooting gallery, with no warning when the next major threat approaches. Dr. Amy Mainzer, principal investigator of NASA's NEO-EYES mission, has revolutionized asteroid detection using infrared space telescopes. Her work has led to the discovery of over 34,000 asteroids and comets, including hundreds classified as potentially hazardous to Earth. People often ask me if I lose sleep worrying about asteroid impacts, she explains. The truth is, the unknown asteroids don't keep me awake. It's the ones we've found and are still studying that sometimes concern me. The psychological toll of cosmic threat detection rarely gets discussed publicly. These astronomers live with the constant awareness that their next observation could reveal an object on a collision course with Earth. Dr. Robert McMillan, who founded the Spacewatch program at the University of Arizona, describes the moment every asteroid hunter dreads. You're processing the night's observations, and suddenly you see something moving fast, on a trajectory that looks uncomfortably close to Earth's orbit. Doctor, your stomach drops as you realize you might be looking at something that could kill millions of people. The work requires extraordinary dedication and precision. Most asteroid hunting happens during the darkest nights of each month, when the moon doesn't interfere with observations. The astronomers work through the night, often staying at remote observatories for weeks at a time, living on coffee and determination, while their computers process millions of images, looking for the telltale streaks that indicate moving objects. Dr. Lindley Johnson, NASA's Planetary Defense Officer, yes, that's a real job title, coordinates the global effort to find and track dangerous asteroids.
His office maintains databases on over 28,000 near-Earth objects and issues alerts when new discoveries pose potential threats. We're essentially conducting a cosmic census, Johnson explains. Every object we catalogue is one less unknown threat that could surprise us.
The international nature of cosmic threat detection has created a unique community of scientists who collaborate across national boundaries with an urgency usually reserved for wartime. Andrea Milani, an Italian mathematician who developed many of the computational techniques used to calculate asteroid orbits, worked closely with colleagues in Russia, Japan, and the United States to refine impact prediction methods. When a potential threat is discovered, observatories around the world immediately begin tracking it, creating a follow-up network that operates with military-like precision. Some of the most important discoveries come from amateur astronomers who have dedicated their lives to cosmic surveillance. Koichi Itagaki, a Japanese amateur astronomer, has discovered more supernovas than almost anyone in history, providing early warnings of stellar explosions that help scientists understand gamma-ray burst risks. His backyard observatory, equipped with automated systems he built himself, operates every clear night, contributing crucial data to professional research programs. The emotional weight of their responsibility affects these astronomers in profound ways. Dr. Don Yeomans, former head of NASA's Near-Earth Object Program, recalls the discovery of asteroid 99942, Hopperfis, in 2004. Initial calculations suggested it had a 1 in 37 chance of hitting Earth in 2029. For several months, we carried the psychological burden of potentially being the messengers of humanity's doom. Even after we refined the orbit and ruled out the 2029 impact, the experience left a lasting impression on everyone involved. Space weather monitoring requires a different type of vigilance, but equal dedication. Dr. Rodney Viereck at NOAA's Space Weather Prediction Center leads a team that monitors the sun 24 hours a day, 365 days a year. Their job is to spot the coronal mass ejections and solar flares that could cripple modern technology. We're like meteorologists, but our weather comes from 93 million miles away and travels at millions of miles per hour, Viereck explains. When we issue a space weather warning, satellite operators and power grid managers around the world take protective action based on our forecasts. The advent of automated detection systems has transformed the field, but human expertise remains irreplaceable. Computers can process millions of images and identify potential threats, but it takes human experience to distinguish between genuine cosmic threats and the false alarms generated by satellite glints, cosmic ray hits on detectors, and processing artifacts. Dr. Eric Christensen, director of the Catalina Sky Survey, has personally discovered over 17,000 asteroids, including hundreds classified as potentially hazardous. Each discovery represents thousands of hours of work by our entire team, he notes. But we never forget that somewhere in our data might be the object that poses a real threat to Earth. That possibility drives everything we do. These cosmic watchers work with the knowledge that their vigilance might be all that stands between humanity and catastrophic surprise. They scan the skies not for glory or recognition, but because someone has to, and they've chosen to accept responsibility for protecting a world that rarely acknowledges their existence. Every clear night, as most of the world sleeps, they stand guard against the darkness, watching for threats that travel silently through the void, hoping that their next discovery will be another harmless space rock rather than humanity's final deadline. At 3:47 a.m. on January 13, 2018, Hawaii emergency management officials sent a message that instantly transformed a tropical paradise into a scene of absolute terror. Ballistic missile threat, inbound to Hawaii. Seek immediate shelter. This is not a drill. For 38 agonizing minutes, over 1 million people believed they were about to die in a nuclear attack. Parents clutched children in bathtubs. Tourists hid in hotel stairwells, and families called loved ones to say goodbye. The message was false. A training exercise button accidentally pushed, but it revealed how quickly modern civilization can collapse when faced with the prospect of cosmic-scale destruction. This terrestrial false alarm pales in comparison to the cosmic close calls that have occurred throughout human history, events where the universe loaded the gun, aimed it at Earth, and came terrifyingly close to pulling the trigger. These near misses serve as stark reminders that we live in a cosmic shooting gallery, where the difference between survival and extinction often comes down to timing, measured in days, hours, or even minutes. On July 23, 2012, Earth experienced what NASA scientists later called the most powerful solar storm in over 150 years, except it missed us entirely. A massive coronal mass ejection, potentially more powerful than the Carrington event of 1859, tore through Earth's orbital path at precisely the spot our planet had occupied just 1 week earlier. If the timing had been different by a mere 7 days, the consequences could have been catastrophic. Dr. Daniel Baker, who led the analysis of this near miss, described it in sobering terms. If it had hit, we would still be picking up the pieces. The estimated damage from this solar storm, had it struck Earth, ranged from $1 - 2 trillion in the United States alone, with recovery times potentially measured in years or decades. Instead, the billion-ton cloud of magnetized plasma sailed harmlessly past our planet and impacted NASA's Stereo-A spacecraft, providing scientists with detailed measurements of what could have been civilization's worst nightmare. The 2012 solar storm wasn't detected until nearly 2 years after it occurred, when researchers analyzing spacecraft data realized how close we had come to technological apocalypse. This delayed recognition highlights a terrifying reality. We might not even know about some cosmic close calls until long after they've passed. Asteroid discoveries frequently provide heart-stopping moments of uncertainty before orbital calculations can rule out impact threats. In October 2017, astronomers discovered 2017 PDC, an asteroid roughly 100–300 meters across, on a trajectory that initial calculations suggested might impact Earth in 2027. For several weeks, as observatories around the world tracked this object and refined its orbit, planetary defense experts quietly prepared for the possibility that they were watching humanity's death warrant hurtle through space. Additional observations eventually ruled out any impact risk, but the discovery process revealed how cosmic threats can materialize with shocking suddenness. The asteroid had been approaching for millions of years, invisible to our detection systems until it came close enough to be spotted by our telescopes. Even then, the uncertainty in its orbit meant that for weeks, scientists couldn't definitively say whether it would miss Earth or trigger the first mass extinction in 66 million years. Perhaps the most unnerving aspect of cosmic close calls is how many threats we discover only after they've already passed. Asteroid 2019, dubbed the City Killer, approached within 70,000 kilometers of Earth, about 1/5 the distance to the Moon, and was discovered less than 24 hours before its closest approach. This 100-meter-wide object was large enough to destroy a major metropolitan area, yet our most sophisticated detection systems provided less than a day's warning. The Chelyabinsk meteor of 2013 demonstrated our blindness to cosmic threats in the most dramatic way possible. The 17-meter asteroid exploded over Russia with the force of 30 atomic bombs, injuring over 1,500 people and damaging thousands of buildings. It was completely undetected by our global asteroid monitoring network, approaching from the direction of the Sun, where it remained invisible until the moment of impact. Video footage from Chelyabinsk shows the psychological impact of a cosmic close call in real time. Dashboard cameras captured the moment when a routine morning commute was interrupted by a flash brighter than the sun, followed by a shockwave that turned windows into deadly projectiles. The audio reveals something even more disturbing: the several seconds of eerie silence between the flash and the arrival of the shockwave, moments when witnesses didn't yet understand that they were experiencing a cosmic attack. Space weather close calls often go unnoticed by the general public, but send shockwaves through the scientific community. In March 1989, a relatively modest geomagnetic storm caused a 9-hour blackout in Quebec, affecting 6 million people. But the same storm nearly triggered much more serious consequences. It induced currents in power grids across North America that came dangerously close to causing permanent damage to critical transformers in the northeastern United States. The Halloween storms of 2003 provided another space weather close call that revealed our technological vulnerability. A series of coronal mass ejections damaged 47 satellites, forced astronauts on the International Space Station to take shelter from radiation, and caused power outages across Europe. GPS systems became unreliable, and some commercial airliners were forced to alter their routes to avoid flying over the poles, where radiation exposure was dangerously high. False alarms in cosmic threat detection create their own category of terror. In 1995, Russia nearly launched nuclear missiles when radar operators detected what appeared to be a submarine-launched ballistic missile, all approaching from the Atlantic. The object was actually a scientific rocket launched from Norway to study the aurora, but the trajectory looked identical to a nuclear attack from a US submarine. For several minutes, the world teetered on the brink of nuclear war because of a cosmic research project. More recently, automated asteroid detection systems have generated false alarms that briefly suggested imminent impact threats. In 2008, asteroid 2008, TC3, was discovered just 19 hours before it hit Earth, but this time the impact prediction was correct. The small asteroid exploded harmlessly over Sudan, becoming the first cosmic impact to be predicted in advance. However, the discovery process revealed how little warning time we might have for larger, more dangerous objects. Perhaps most sobering is the realization that for every cosmic close call we've detected and studied, there may be others that passed unnoticed. Our detection capabilities are improving rapidly, but they still have significant blind spots and limitations. Objects approaching from certain angles, very dark asteroids that reflect little sunlight, and solar storms that occur during periods when our monitoring satellites are not optimally positioned, could all slip past our surveillance network. These close calls serve as wake-up calls, reminding us that cosmic catastrophe isn't a matter of if, but when. Each near miss represents a roll of the cosmic dice that came up in humanity's favor, but the dice are still rolling, and eventually our luck will run out. On September 26, 2022, humanity fired its first shot in the war against cosmic catastrophe. NASA's DART spacecraft, traveling at over 6 kilometers per second, deliberately crashed into the asteroid Dimorphos with the force of a small nuclear weapon. The impact changed the asteroid's orbital period by 32 minutes, proof that human technology can indeed alter the trajectory of cosmic threats. For the first time in our species' history, we had demonstrated that we are not helpless victims waiting for the universe to destroy us. The Double Asteroid Redirection Test DART mission represents a fundamental shift in how humanity approaches cosmic threats. Instead of simply watching and hoping for the best, we've begun developing the capability to fight back against the forces that have caused mass extinctions throughout Earth's history. The success of DART validated the kinetic impactor technique, essentially using a spacecraft as a cosmic bullet to nudge dangerous asteroids off collision courses with Earth. But DART was just the proof of concept. The real asteroid deflection systems now under development represent some of the most ambitious engineering projects in human history. NASA's proposed asteroid redirect mission would use a robotic spacecraft to capture a small asteroid or boulder from a larger asteroid and move it into orbit around the Moon, where it could be studied by astronauts and used to test deflection techniques. The physics of asteroid deflection is more complex than simply hitting space rocks with spacecraft. The effectiveness of any deflection attempt depends critically on the asteroid's composition, structure, and rotational state. A solid metallic asteroid responds differently to impacts than a loosely bound rubble pile held together primarily by gravity. Some asteroids spin so rapidly that impacts might cause them to break apart rather than change trajectory, potentially creating multiple smaller threats instead of eliminating the original danger. This is why missions like the European Space Agency's HERA are crucial to developing effective planetary defense capabilities. HERA will visit the Dimorphos asteroid system to study the aftermath of the DART impact in detail, measuring how the collision affected not just the asteroid's orbit, but also its internal structure and composition. This data will inform the design of future deflection missions and help scientists understand which techniques work best for different types of asteroids. Nuclear deflection represents the most powerful tool in our planetary defense arsenal, though it comes with significant technical and political challenges. Unlike the dramatic explosions depicted in science fiction movies, nuclear asteroid deflection would likely involve detonating nuclear devices near an asteroid rather than on its surface, using the X-ray radiation from the explosion to vaporize surface material and create a rocket-like thrust that pushes the object off its collision course. The technical challenges of nuclear deflection are formidable. The nuclear device must be precisely positioned and timed to maximize the deflection effect, while minimizing the risk of fragmenting the asteroid. The spacecraft delivering the weapon must be capable of autonomous operation across interplanetary distances, since communication delays make real-time control impossible. International treaties governing nuclear weapons in space add additional complexity to any nuclear deflection mission. Ion propulsion systems offer a gentler but potentially more efficient approach to asteroid deflection. These systems, which use electric fields to accelerate charged particles and generate thrust, can operate continuously for months or years, gradually changing an asteroid's velocity with minimal risk of fragmentation. The European Space Agency's proposed Don Quixote mission would test this technique by attaching an ion drive to a target asteroid and measuring the resulting orbital changes. Gravity tractors represent perhaps the most elegant asteroid deflection concept, a spacecraft that hovers near a dangerous asteroid for months or years, using its gravitational attraction to gradually pull the object off its collision course. While the gravitational forces involved are tiny, the technique has the advantage of working on any type of asteroid regardless of composition or structure. The main limitation is time. Gravity tractors require years or decades of operation to produce significant orbital changes. Solar sails and mirrors could harness the pressure of sunlight to deflect asteroids, either by attaching reflective materials to the asteroid's surface or by positioning large mirrors to focus sunlight on specific areas. The Yarkovsky effect, where absorbed and re-radiated sunlight creates a tiny but persistent thrust, could be enhanced or redirected using these techniques. The timing of deflection attempts is critical to their success. The earlier a deflection is attempted, the smaller the velocity change needed to prevent an impact. An asteroid diverted 10 years before a predicted impact needs only a tiny nudge to miss Earth entirely, while the same asteroid diverted just 1 year before impact might require massive forces that could fragment it into multiple dangerous pieces. Current planetary defense plans envision a graduated response system based on the size and warning time of the threat. Small asteroids detected with years of warning time might be deflected using ion propulsion or gravity tractors. Larger threats with shorter warning times could require nuclear deflection. The most dangerous scenario, a large asteroid detected with less than a year of warning, might require multiple simultaneous deflection attempts using all available techniques. The international coordination required for asteroid deflection missions presents significant challenges. No single nation has the resources to defend Earth from all possible cosmic threats, and successful deflection requires global cooperation in detection, tracking, and response. The United Nations Office for Outer Space Affairs has begun developing frameworks for international cooperation on planetary defense, but the legal and political complexities remain formidable. Perhaps most importantly, effective planetary defense requires sustained investment in detection systems, deflection technologies, and international cooperation long before any specific threat is identified. The infrastructure needed to deflect dangerous asteroids takes years or decades to develop and deploy, meaning that we must build these capabilities based on statistical threats rather than known dangers. The success of DART proved that humans are no longer helpless against cosmic threats, but it also revealed how much work remains to build a comprehensive planetary defense system capable of protecting Earth from the full range of potential asteroid impacts. The race to harden our infrastructure against space weather continues, driven by the recognition that our technological civilization has become exquisitely vulnerable to cosmic forces. Each protective measure we implement represents a small victory against the universe's capacity for destruction. But the scale of the challenge requires nothing less than rebuilding the foundations of modern society with space weather in mind. Perhaps most promising are the distributed energy systems that could replace our vulnerable centralized power grids. Microgrids, equipped with local solar panels, batteries, and backup generators, can operate independently during space weather events, maintaining power to critical facilities like hospitals and emergency services, even when the main grid fails. These systems are inherently more resilient because they don't depend on long transmission lines that act as antennas for geomagnetic disturbances. Water treatment and distribution systems are being redesigned with space weather resilience as a primary consideration. New facilities include backup power systems that can operate for weeks without external electricity, manual override systems that allow critical functions to continue without computer control, and hardened communication systems that can coordinate emergency response even when normal networks fail. The hardening process reveals uncomfortable truths about our infrastructure's fragility. Many critical systems were designed during an era when space weather was poorly understood, while creating vulnerabilities that are expensive and difficult to address. The massive transformers that regulate electrical distribution, some weighing hundreds of tons, cannot be easily protected or quickly replaced. Upgrading these systems requires investments measured in hundreds of billions of dollars and decades of sustained effort. Yet the alternative, accepting vulnerability to space weather catastrophe, is unthinkable. Each hardening measure, no matter how expensive, is an insurance policy against civilization-ending collapse. Despite all our technological prowess, our growing understanding of cosmic threats, and our expanding arsenal of planetary defense systems, there remain cosmic forces so powerful and so sudden that human ingenuity simply cannot overcome them. These represent the ultimate limits of our species' ability to protect itself from the universe's most violent phenomena. Gamma-ray bursts from nearby stellar explosions stand as perhaps the most insurmountable cosmic threat. When a massive star within 8,000 light-years of Earth collapses into a black hole and fires its jets of destruction in our direction, we face a weapon that travels at the speed of light, carries more energy than our sun will produce in its entire lifetime, and provides absolutely no advance warning. The gamma rays arrive simultaneously with our first detection of the event, meaning that by the time we know a nearby GRB has occurred, we're already being irradiated. No shielding technology can protect against such an onslaught. The most energetic gamma rays can penetrate several meters of lead, making it impossible to create effective shelters for large populations. The radiation doses would be lethal to most complex life forms within hours or days, and the atmospheric damage would persist for years. There is simply no defense against a cosmic weapon that can sterilize planets from thousands of light-years away. Hypernova explosions, stellar deaths, even more energetic than typical supernovas, represent another unstoppable threat. These events can occur when stars over 130 times the mass of our Sun undergo complete gravitational collapse, releasing energy equivalent to hundreds of ordinary supernovas. The radiation and particle bombardment from a hypernova within our local stellar neighborhood could overwhelm Earth's magnetosphere and atmosphere so completely that no technological intervention could preserve habitability. The most terrifying aspect of these stellar explosions is their unpredictability. Stars can appear stable for millions of years before suddenly entering their final collapse phase. Eta Carinae, the massive star, 7,500 light-years away, that many astronomers consider our most dangerous stellar neighbor, could explode tomorrow or continue burning for another million years. We have no way to predict the timing of stellar deaths with the precision needed for effective planetary defense. Large asteroid impacts represent threats that we are only beginning to develop the capability to address. While the DART mission proved that we can deflect small asteroids given sufficient warning time, objects larger than a few kilometers across would require deflection forces beyond our current technological capabilities. The asteroid that killed the dinosaurs was roughly 10 kilometers wide. Deflecting such an object would require nuclear explosions, orders of magnitude more powerful than anything in our current arsenals, or deflection attempts begun decades before the predicted impact. Even more challenging are the stealth asteroids, dark objects with very low reflectivity that remain invisible to our detection systems until they're dangerously close to Earth. Long-period comets, arriving from the outer solar system on highly elliptical orbits, can approach at speeds exceeding 70 kilometers per second and might be detected only months before potential impact. At such velocities, with such short warning times, deflection becomes nearly impossible, regardless of the technology employed. Coronal mass ejections of extreme magnitude represent space weather threats that could overwhelm any protective measures we might implement. While we can harden our infrastructure against moderate space weather events, truly extreme solar storms, like the Carrington event of 1859, or potentially more powerful events recorded in ice core data, could induce electrical currents strong enough to melt the protective systems themselves. The mathematical modeling is sobering. A solar storm 10 times more powerful than Carrington-level events could induce currents in power grids that would destroy transformers even if they were disconnected from the system. The sheer magnitude of electromagnetic energy involved would overwhelm any realistic protection scheme, potentially leaving entire continents without electrical power for years or decades. Perhaps most fundamentally limiting is the speed of light constraint that governs all cosmic threats. Many of the most dangerous phenomena in the universe, gamma-ray bursts, massive solar flares, hypernova explosions, announce their arrival with the very radiation that can kill us. This means we can never have more warning than the time it takes light to travel from the source to Earth, which for nearby threats might be measured in minutes rather than the days or weeks needed for effective response. The scale mismatches between cosmic forces and human technology represent another insurmountable challenge. The energy involved in major cosmic events exceeds human energy production by factors of trillions or quadrillions. A single large solar flare releases more energy than human civilization has produced throughout its entire history. We are trying to defend against weapons that dwarf our capabilities by ratios so large they become almost meaningless. Even our most ambitious planetary defense concepts pale in comparison to the threats they're designed to address. The most powerful nuclear weapons ever built release energy equivalent to about 50 megatons of TNT. The Chicxulub asteroid impact that killed the dinosaurs released energy equivalent to 100 trillion tons of TNT, 2 million times more powerful than our largest nuclear weapons. Deflecting such an object would require technologies that remain firmly in the realm of science fiction. Time constraints add another layer of impossibility to cosmic threat mitigation. All developing and deploying planetary defense systems requires decades of sustained investment and international cooperation. But cosmic threats operate on timescales that range from seconds to millions of years, with no regard for human planning cycles or technological development schedules. We might identify a dangerous asteroid today that will impact Earth in 6 months. Far too little time to develop and deploy effective deflection systems. The randomness of cosmic threats makes comprehensive defense planning nearly impossible. We can prepare for the threats we understand and can predict, but the universe regularly produces phenomena that exceed our models and expectations. The most dangerous cosmic events might be ones we haven't yet discovered or understood, making it impossible to develop appropriate defenses. Perhaps most sobering is the realization that some cosmic threats are so rare and so powerful that they represent evolutionary filters, events that prevent the development of advanced civilizations by periodically sterilizing planets and resetting the biological clock. If gamma-ray bursts, hypernova explosions, or extreme asteroid impacts occur frequently enough in cosmic terms, they might explain why we don't see evidence of other advanced civilizations in our galaxy. In the face of these ultimate cosmic threats, human ingenuity reaches its absolute limits. Homing deflects small asteroids, protect against moderate space weather, and shelter from minor radiation exposure. But when the universe decides to deploy its most powerful weapons, we remain as vulnerable as our ancestors who watched the skies with wonder and terror, hoping that the forces beyond their control would continue to spare their small, fragile world. The mathematics of cosmic catastrophe are as elegant as they are terrifying. Somewhere in the intersection of probability theory, astronomical observation, and historical geology lies the cold calculation of humanity's odds of survival, numbers that simultaneously offer comfort and existential dread. Let's start with asteroid impacts, where the statistics are most reliable, because we can observe the evidence written in Earth's geological record. Kilometer-sized asteroids, the civilization killers, capable of ending technological society, strike Earth roughly once every 500,000 to 1 million years. This might sound reassuringly rare, but consider that modern human civilization is only about 10,000 years old. We've existed as a technological species for less than 2% of the interval between major impacts. The probability calculations become more unsettling when we consider that these are average intervals, not predictable schedules. The randomness of cosmic impacts means that 2 civilization-killing asteroids could strike within a century of each other, or we might go 2 million years without a major impact. It's like playing cosmic roulette, where we don't know when the wheel will stop spinning, but we know that eventually our number will come up. For smaller but still devastating asteroids, the 100-meter city killers that could destroy metropolitan areas, the odds shift dramatically. These objects strike Earth approximately once every 10,000 to 20,000 years. Given that we've been building large cities for only a few thousand years, we've been remarkably fortunate. The Tunguska event of 1908, which flattened 2,000 square kilometers of Siberian forest, demonstrates what happens when these cosmic bullets find their target. Statistical analysis of our current asteroid detection efforts reveals sobering gaps in our cosmic situational awareness. We've identified roughly 90% of the kilometer-sized near-Earth asteroids, but less than 30% of the 100-meter objects that could cause regional devastation. This means that at any given moment, there are thousands of city-killer asteroids whose orbits we don't know, any one of which could be discovered on a collision course with Earth. Gamma-ray bursts present, perhaps the most challenging statistical puzzle in cosmic threat assessment. Based on our observations of GRBs in distant galaxies, astronomers estimate that a potentially lethal gamma-ray burst occurs in our galaxy roughly once every 100,000 to 1 million years. Took more than 1 million years, but the directional nature of these cosmic weapons adds complexity to the calculations. Only GRBs, whose jets happen to point toward Earth, pose a significant threat. The geometric probability that a galactic GRB will point its jets at Earth is roughly 1 in 1,000, based on the narrow opening angles of these cosmic weapons. This means that while GRBs might occur in our galaxy every few 100,000 years, only 1 in 1,000 would pose a direct threat to Earth. The combined probability suggests we might face a dangerous GRB roughly once every 100 million to 1 billion years. Solar storm statistics offer both reassurance and concern. Major geomagnetic storms like the Carrington event of 1859 occur roughly once every 150 years, based on historical records and ice core data. This suggests we're actually overdue for another major space weather event. More extreme solar storms, potentially capable of causing permanent damage to technological infrastructure, might occur once every 500 to 1,000 years. The challenge with space weather statistics is that our technological vulnerability has increased exponentially over the past century. A Carrington-level event in 1859 disrupted telegraph systems, but the same storm today could cause trillions of dollars in damage and leave billions without power for extended periods. We're conducting an uncontrolled experiment in technological vulnerability to space weather. Multiple threat scenarios add another layer of complexity to survival statistics. The probability that we'll face at least one major cosmic threat in the next 1,000 years, considering asteroids, GRBs, and solar storms, approaches statistical certainty. The mathematics of multiple independent threats working against us are unforgiving. Even if each individual threat has a low annual probability, the cumulative odds over decades and centuries become substantial. Perhaps most sobering is the realization that these statistics are based on incomplete data. We've only been seriously studying cosmic threats for a few decades, and our historical record extends back just a few thousand years for most phenomena. Ancient cosmic catastrophes that left no clear geological signature might have occurred more frequently than our current models suggest. The statistics also assume that cosmic threat rates remain constant over time, but this may not be accurate. Our solar system's position in the galaxy changes over millions of years, potentially exposing us to different levels of cosmic radiation and stellar explosion risks. Climate changes on the Sun itself could alter the frequency and intensity of space weather events. When confronted with these numbers, the remarkable fact isn't that cosmic catastrophes are possible, it's that complex life and human civilization have managed to evolve and thrive despite them. We exist in the gaps between cosmic disasters, in the brief, peaceful interludes when the universe's weapons of mass destruction happen to be pointed elsewhere. The question that haunts every discussion of cosmic threats isn't whether they'll occur, but when, or the timescales involved range from minutes to millions of years, creating a paradox where some threats could materialize tomorrow, while others may not manifest for geological ages. Understanding these temporal patterns is crucial for prioritizing our planetary defense efforts and managing the psychological burden of living under constant cosmic threat. Asteroid impacts operate on timescales that span human comprehension. Small meteors, like the one that exploded over Chelyabinsk in 2013, arrive constantly. Earth is struck by house-sized objects several times a year, though most explode harmlessly in the atmosphere or impact uninhabited areas. City-killer asteroids, capable of regional devastation, follow a more ominous timeline. Statistical models suggest one will strike a populated area roughly once every few thousand years. The terrifying aspect of asteroid timescales is their complete unpredictability on human timeframes. The last major impact, the Tunguska event of 1908, occurred 115 years ago, which might suggest we're due for another. But cosmic statistics don't work like clockwork. The next Tunguska scale impact could happen tomorrow, or we might wait another 1,000 years. The randomness makes planning and preparation incredibly challenging. For the truly civilization-ending asteroids, objects larger than a kilometer across, the timescales extend to hundreds of thousands or millions of years between impacts. This creates a false sense of security. Such events are so rare that human institutions and even entire civilizations rise and fall in the intervals between major impacts. Yet the geological record shows they do occur with statistical regularity, and when they do, they reset the entire evolutionary timeline. Solar storm timescales follow more predictable patterns tied to the sun's 11-year activity cycle, with dangerous variations. Minor geomagnetic storms occur several times per year during solar maximum periods, while major storms like the 1989 Quebec blackout happen roughly once per decade. The most extreme events, Carrington-level storms, appear to occur once or twice per century, though the historical record is too short to establish precise frequencies. What makes solar storm timing particularly relevant is that we're approaching solar maximum in the current cycle, expected around 2025. This doesn't guarantee a major space weather event, but it does increase the statistical likelihood. More concerning are the rogue, solar storms that can occur even during periods of supposedly low solar activity, defying our predictive models and catching our space weather monitoring systems off guard. Gamma-ray bursts operate on the most extreme timescales in cosmic threat assessment. A dangerous GRB in our galactic neighborhood might occur once every 100 million to 1 billion years, timescales so vast that complex life could evolve, flourish, go extinct, and evolve again multiple times between events. Yet, when they do occur, their effects are instantaneous. The gamma radiation travels at the speed of light, providing no advance warning and no time for protective measures. The temporal disconnect between GRB frequency and human civilization creates a unique form of existential risk. We might go thousands of human generations without facing this threat, or a nearby star might collapse tomorrow and end complex life on Earth within hours. The complete unpredictability makes GRBs simultaneously the least likely and most devastating cosmic threat we face. Supervolcanic eruptions, while not strictly cosmic threats, operate on timescales that intersect meaningfully with human civilization. The Yellowstone supervolcano has erupted approximately every 600,000 to 800,000 years, and the last eruption occurred about 640,000 years ago. While this might suggest we're approaching another eruption, the uncertainty in these estimates spans hundreds of thousands of years. The cascading effects of cosmic threats extend their timescales far beyond the initial events. A major asteroid impact might last only seconds, but the resulting impact winter could persist for years or decades. The atmospheric damage from a nearby gamma-ray burst could take centuries to fully heal. The long-term genetic effects of radiation exposure could influence evolution for thousands of generations. Climate change adds complexity to cosmic threat timescales by potentially altering Earth's vulnerability to space weather and atmospheric disruption. A planet already stressed by changing climate conditions might be more susceptible to the additional pressures that cosmic events impose on global ecosystems and human infrastructure. Technological change accelerates some threat timescales while extending others. Our growing dependence on vulnerable electronic systems means that space weather events that would have been minor inconveniences a century ago could now cause civilization-ending damage. Conversely, our developing planetary defense capabilities might eventually allow us to deflect asteroid threats that would have been unstoppable just decades ago. The psychological challenge of cosmic threat timescales is managing preparedness for events that might not occur for generations, while maintaining vigilance for threats that could materialize with little or no warning. Emergency planning operates on timescales of days to months, while cosmic threats operate on scales ranging from minutes to millennia. Perhaps most unsettling is the realization that multiple cosmic threats could converge on similar timescales. The probability of facing both a major solar storm and a dangerous asteroid impact within the same decade is low but not negligible. Such coincidences could overwhelm our response capabilities and multiply the damage beyond what any single threat might cause. The when of cosmic catastrophe remains fundamentally unknowable, hidden in the intersection of chaotic celestial mechanics, stellar evolution, and the random walk of cosmic events. We can calculate probabilities and estimate frequencies, but the universe operates on its own schedule, indifferent to human plans and preparations. The only certainty is that somewhere in our future, whether measured in years, centuries, or millennia, cosmic forces will again reach down from space to test our planet's resilience and our species' ingenuity. As we stand at the threshold of becoming a spacefaring civilization, equipped with more knowledge about cosmic threats than any previous generation in human history, we face the ultimate question that has haunted our species since we first looked up at the stars. Can humanity ultimately survive in a universe that seems designed to destroy us? The evidence presents a sobering paradox. On one hand, life on Earth has persevered through cosmic catastrophes that would challenge even our current technological capabilities. The planet has survived gamma-ray bursts that sterilized the upper atmosphere, asteroid impacts that vaporized continents, solar storms that stripped away portions of the atmosphere, and stellar explosions that bathed our world in lethal radiation. Through all of these cosmic assaults, life found a way to survive, adapt, and eventually flourish. Yet the life that survived these events was fundamentally different from the complex, interconnected civilization we've built today. When cosmic catastrophes struck in the past, they eliminated the most complex and specialized forms of life, leaving behind simpler organisms that could survive in degraded environments. The dinosaurs, masters of their world for 160 million years, couldn't survive one bad day when an asteroid reset the planetary ecosystem. Intelligence, sophistication, and ecological dominance offered no protection against cosmic forces. Modern human civilization represents an unprecedented experiment in complexity and vulnerability. We've created a global society that depends on technologies and systems that didn't exist even a century ago. Our food production depends on GPS-guided tractors, satellite-monitored weather systems, and global supply chains that can be disrupted by space weather events thousands of miles away. Our financial systems depend on precise timing signals from satellites orbiting in the radiation-filled vacuum of space. This technological sophistication gives us capabilities that no previous Earth species possessed. We can see cosmic threats coming, understand their mechanisms, and in some cases, develop defenses against them. The DART mission proved that we can deflect dangerous asteroids. Our space weather monitoring systems provide warnings that allow us to protect critical infrastructure. Our growing understanding of gamma-ray bursts and supervolcanic eruptions helps us assess and prepare for low-probability, high-impact events. But our technological capabilities also create new vulnerabilities that make us potentially more fragile than our ancestors. A space weather event that would have been merely a spectacular aurora display to medieval Europeans could collapse our technological civilization and leave billions without access to food, water, medical care, or communication systems. We've created a civilization that operates at the speed of light and depends on the stability of space-based infrastructure. The mathematical realities are unforgiving. No matter how sophisticated our planetary defense systems become, we cannot defend against all possible cosmic threats. Gamma-ray bursts from nearby stellar explosions travel at the speed of light and provide no advance warning. Hypernova explosions can sterilize planets from thousands of light years away. Truly massive asteroid impacts require deflection forces beyond any reasonable technological capability. Interacting with known pieces into binary hypernova explosions can sterilize planets from thousands of light years away. Yet perhaps the question of ultimate survival isn't about defending against every possible cosmic threat. It's about building resilience and redundancy that allows human civilization to survive the inevitable cosmic disasters. Intrable, cividiscipline denu and shatagin. Yet perhaps the question of ultimate survival isn't about defending against every possible cosmic threat. It's about building resilience and redundancy that allows human civilization to survive the inevitable cosmic disasters. It's about building resilience and redundancy that allows human civilization to survive the inevitable cosmic disasters. The key may lie not in preventing all cosmic catastrophes, but in ensuring that some portion of humanity can survive and rebuild when catastrophes occur. The emerging concept of planetary backup systems suggests one approach to cosmic resilience. Self-sustaining lunar colonies, protected by underground construction and closed-loop life support systems, could serve as insurance policies against Earth-based catastrophes. Mars settlements, isolated from Earth by millions of miles and protected by different atmospheric and magnetic conditions, could preserve human civilization even if cosmic events sterilize our home planet. Distributed space habitats, positioned throughout the solar system, could provide multiple independent backups for human civilization. O'Neill cylinders, rotating space stations that generate artificial gravity through centrifugal force, could support millions of people in environments completely isolated from cosmic threats that affect planetary surfaces. These habitats could be positioned at Lagrange points, asteroid locations, or in orbit around gas giant moons, creating a distributed human presence that no single cosmic event could eliminate entirely. The preservation of human knowledge and culture presents another dimension of cosmic survival. Digital archives, genetic banks, and cultural repositories distributed across multiple worlds and space habitats could ensure that human achievements survive even catastrophic losses of population and infrastructure. The challenge is creating storage and retrieval systems that can operate across the timescales involved in cosmic catastrophes, potentially thousands of years between disaster and recovery. Genetic and biological adaptation might offer long-term solutions to cosmic survival challenges. Advances in genetic engineering could potentially create human variants better adapted to high radiation environments, low gravity conditions, or the psychological stresses of space-based living. While such modifications raise profound ethical questions, they might be necessary for long-term survival in a cosmic environment that regularly deploys weapons of mass destruction. The development of artificial intelligence and robotic systems capable of autonomous operation across interstellar distances could create backup systems for human civilization that operate independently of biological survival requirements. Self-replicating robotic systems could preserve human knowledge and culture, even if biological humans don't survive particular cosmic catastrophes, potentially rebuilding human civilization using genetic archives and artificial reproduction technologies. Self-replicating robotic systems could preserve human knowledge and culture, even if biological humans don't survive particular cosmic catastrophes. Perhaps most importantly, cosmic survival requires a fundamental shift in how we think about human civilization and its relationship to the universe. Instead of viewing Earth as a permanent home base, we may need to embrace a nomadic model of civilization that treats planets, moons, and space habitats as temporary way stations in an ongoing journey through space and time. The universe has already shown us its power to end civilizations. The absence of detectable alien civilizations in our galaxy might indicate that cosmic threats regularly prevent the development of advanced technologies or force civilizations to adopt survival strategies that make them difficult to detect. We may be facing evolutionary filters that most species cannot pass, cosmic tests that determine which civilizations earn the right to spread beyond their home planets. The ultimate question of whether humanity can survive the universe's worst may depend not on our ability to prevent cosmic catastrophes, but on our wisdom in preparing for them. The species that learns to live with cosmic threats, rather than simply hoping to avoid them, may be the one that ultimately inherits the galaxy. In the end, our survival may require accepting that we live in a dangerous universe where catastrophic events are not anomalies to be prevented, but normal features of cosmic evolution to be planned for, adapted to, and ultimately transcended. The question isn't whether we can make the universe safe for humanity, it's whether we can make humanity resilient enough to survive in an unsafe universe. And an unsafe universe. The answer to that question will determine whether we join the ranks of civilizations that learn to thrive among the stars, or become another cautionary tale written in the geological record of a small, fragile planet that briefly believed it was safe. We've journeyed through the cosmos's arsenal of destruction, from gamma-ray bursts that can sterilize star systems to solar storms that threaten our technological civilization, from asteroid impacts that have already reset evolution to the invisible radiation that dismantles life molecule by molecule. The evidence is overwhelming. We are not safe. But perhaps that's not the point. Perhaps the true measure of humanity isn't our ability to hide from cosmic forces, but our courage to face them. We've built detection systems that scan the skies for threats. We've developed technologies to deflect dangerous asteroids. But perhaps that's not the point. Perhaps the true measure of humanity isn't our ability to hide from cosmic forces. We're hardening our infrastructure against space weather. We're taking our first steps toward becoming a multi-planetary species. The universe may be vast and violent, but it has also produced something remarkable, a species capable of understanding its own vulnerability and fighting back against forces that dwarf our comprehension. We are fragile, yes, but we are not helpless. The cosmic sword hangs over our heads, as it always has. The difference is that now we see it coming, and for the first time in Earth's history, we're reaching up to deflect it. The question isn't whether we'll face cosmic catastrophe. The question is whether we'll be ready when we do. Our survival depends on the answer. What keeps you awake at night? Earthly concerns, or the thought that right now cosmic forces beyond our control could be racing toward us at the speed of light? Share your thoughts in the comments below. If this journey through our cosmic vulnerabilities has left you both humbled and determined, hit that like button and subscribe for more explorations into the universe's most profound mysteries. Your support helps us continue investigating the forces that shape our existence. The cosmos holds infinite stories of wonder and terror, each more remarkable than the last. Ready to continue exploring? Click here to discover our complete collection of cosmic documentaries, where every video reveals another chapter in humanity's ongoing dialogue with the universe itself.